The Ultimate Production Incident Masterclass for modern Java application support engineers, Spring Boot, and Kubernetes.
Welcome to the Ultimate Production Incident Masterclass for modern Java application support engineers, Spring Boot, and Kubernetes. In this reference grade series, we solve 195 real-world production incidents inspired by enterprise Spring Boot microservices running on Kubernetes. Every incident follows a structured 5-phase war room framework: initial assessment, investigation, root cause analysis, resolution with MTTR-focused recovery, and recurrence prevention, followed by realistic war room follow-up questions that mirror modern technical interviews.
Modern Java application support, stack Spring Boot and Kubernetes.
The production incidents throughout this masterclass are based on a modern enterprise technology stack commonly used across cloud-native Java applications. 1. Java 17 or 21. Modern LTS Java runtimes, JVM tuning, garbage collection, and performance troubleshooting. 2. Spring Boot. Enterprise application framework powering REST APIs, dependency injection, security, and microservices. 3. Kubernetes. Container orchestration platform responsible for deployments, scaling, health probes, and production recovery. 4. Docker. Container runtime used to package, ship, and run Spring Boot applications consistently across environments. 5. Helm. Kubernetes package manager used to deploy and version production applications through reusable charts. 6. Jenkins or GitHub Actions. CI and CD platforms responsible for automated builds, testing, and production deployments. 7. GitOps. Infrastructure and application deployments managed through version-controlled Git repositories. 8. REST APIs and microservices. Distributed service architecture requiring resilient communication, serialization, and fault tolerance. 9. Kafka. Event streaming platform powering asynchronous messaging and enterprise event-driven architectures. 10. PostgreSQL or Oracle. Enterprise relational databases supporting transactional workloads, connection pools, and SQL performance tuning. 11. RDS. High performance in-memory data store used for caching, distributed locks, sessions, and idempotency. 12. Prometheus and Grafana. Monitoring and observability platforms used for metrics, alerting, dashboards, and incident detection. 13. Spring Web Flux. Reactive programming framework for building high-throughput, non-blocking microservices. Every production incident throughout this masterclass is investigated and resolved within this modern enterprise Java application support ecosystem. Here is how these 195 production incidents are divided into a 4-part masterclass series. Part 1. This video: Java runtime, JVM internals, and concurrency 51 incidents. Covers application startup failures, crash loop backoffs, JVM memory management, garbage collection, CPU bottlenecks, thread deadlocks, and Java concurrency troubleshooting chapters 1 to 3. Part 2. Spring Boot framework, databases, and reactive web flux 49 incidents. Covers Spring Boot runtime failures, dependency injection, health probes, database connectivity, ORM, REST APIs, serialization, and reactive programming chapters 4 to 7. Part 3. Linux OS, Kubernetes, and Kafka event streaming 55 incidents. Covers Linux operating system troubleshooting, Kubernetes production incidents, networking, TLS, service mesh fundamentals, and Kafka event streaming chapters 8 to 11. Part 4. Observability, Vault security, and P1 war room leadership 40 incidents. Covers monitoring, distributed tracing, JVM profiling, secrets management, disaster recovery, active-active failover strategies, and enterprise P1 incident leadership chapters 12 to 15. Let's dive into Part 1. Java runtime, JVM internals, and concurrency.
Part 1. Java application runtime, JVM internals, and concurrency.
Welcome to Part 1. In this 51 incident masterclass, we investigate failures originating inside modern Java applications and the Kubernetes runtime that hosts them. We troubleshoot application startup failures, JVM memory issues, garbage collection, CPU bottlenecks, thread deadlocks, thread contention, and Java concurrency failures. If a production incident originates within the Java runtime, JVM, application startup lifecycle, or concurrent execution model, you will find the complete troubleshooting blueprint in Part 1. Part 1 categories, overview categories 1 to 3. Category 1. Application startup, CI and CD and deployments 18 incidents. Category 2. JVM, Heap, GC and Java platform 18 incidents. Category 3. CPU, threads and concurrency 15 incidents. Let's dive into Category 1.
Category 1. Application startup, CI and CD and deployments.
Modern Java applications are typically deployed as Spring Boot microservices running on Kubernetes. The most vulnerable period begins immediately after a production release, when deployment succeeds but the application fails to become healthy. In this category, we investigate 18 production incidents covering startup failures, crash loop back-off loops, readiness probe failures, configuration drift, missing secrets, deployment strategies, database migrations, config server failures, and scheduled job startup issues.
Category 1. Incidents 1 to 18.
The post-release deployment window is the most high-risk phase in application support. The following 18 incidents cover critical failure modes that occur immediately after code hits production, including crash loop backoffs, local versus prod environment drift, missing secret manifests, flyway database locks, blue-green routing errors, and silent background job failures. Here are the 18 deployment incidents you are going to master in this category. 1. Spring Boot application suddenly fails to start after deploying a new version. Crash loop back off. 2. Application starts locally but crashes immediately in production. 3. Deployment succeeds but all health checks fail. 4. Application remains in starting state indefinitely. 5. Service starts successfully but exits within a few seconds. 6. Missing environment variable causes production startup failure. 7. Configuration changes work in dev but fail in prod. 8. Rolling deployment leaves half the users receiving HTTP 500 errors. 9. Deployment introduces incompatible library versions. 10. Emergency rollback after failed production deployment. 11. Blue-green deployment routes traffic incorrectly. 12. Canary deployment exposes hidden production bugs. 13. Flyway or liquid-based migration locks production tables. 14. Artifact repository nexus/artifactory timeout breaks deployment. 15. Docker image contains incorrect JVM configuration. 16. Startup fails because config server is unavailable. 17. Feature flag activation breaks live production. 18. Deployment succeeds but scheduled jobs stop running. Finally, let's dive into Production Incident 1.
Production Incident 1. During a scheduled weekend release window, a new version of the Spring Boot payment application was deployed to production. Although the deployment pipeline completed successfully, all Kubernetes pods immediately failed health checks and entered crash loop back off, resulting in a P1 outage with 100% request failure for customer transactions. Business stakeholders joined the incident bridge within minutes because payment processing was completely unavailable across all production regions. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this incident?
Answer: during a production outage like this, my priority is to restore customer service safely while preserving enough diagnostic evidence to identify the root cause. I would follow the structured 5-phase incident response process like below. Phase 1. Initial assessment scope and impact. 1. Verify if all pods are affected or only newly deployed instances. 2. Check if readiness and liveness probes are actively failing. 3. Confirm whether the outage is global or isolated to specific regions. 4. Review monitoring dashboards to determine when the failure started and how many customer transactions are impacted. Phase 2. Investigation and evidence gathering. 1. Review application startup logs using kubectl logs to capture unhandled exceptions. 2. Inspect pod events using kubectl describe pod to identify restart reasons. 3. Verify attached config maps and secrets to ensure environment variable alignment. 4. Compare recent CI and CD deployment diffs against the previous working release. Phase 3. Root cause analysis. 1. Evidence collected. Application startup logs showed failed to configure data source. Could not resolve placeholder spring_datasource_password. 2. Primary root cause. Spring_datasource_password was accidentally omitted from the production secret manifest during pipeline execution. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Execute kubectl rollout undo to rollback to the last known stable release and restore customer traffic instantly. 2. Permanent resolution. Re-inject the missing database password secret into the cluster vault and re-trigger deployment. 3. Validation. Confirm pods are healthy, readiness probes green, customer transactions processing and monitoring stable. Phase 5. Recurrence prevention. 1. Add automated pre-deployment secret validation gates in the CI and CD pipeline. 2. Implement automated deployment smoke tests before routing production traffic. 3. Update deployment runbooks for rapid secret verification. Pro tip interview insight. In a real incident, prioritize restoring service immediately via rollback over spending hours fixing a broken deployment in place. Always preserve pod logs before deleting failed pods.
Follow up when expected. A logical continuation of the incident. When investigating the crash loop backoff state, which specific Kubernetes commands and logs would you check first to isolate the error?
Answer: I would immediately run kubectl describe pod to check for specific container exit codes and failure events like create container config error or killed. Because the pod is continuously crashing, the current logs might be empty. Therefore, I would execute kubectl logs -- previous to capture the exact Java stack trace from the crashed container right before it terminated, specifically looking for Spring Boot initialization exceptions, like a data source instantiation failure.
Follow up 2 deeper. Experienced tester. How would you confirm whether the crash is caused by a Kubernetes infrastructure issue rather than an application-level Spring Boot defect?
Answer: I differentiate them by analyzing exit codes and readiness probes. If the pod description shows network timeouts pulling the Docker image, or scheduling errors due to insufficient node resources, it is purely infrastructure. However, if the container pulls successfully but exits with code 1, or if the Spring Boot actuator/health endpoint fails to return a 200 OK before the liveness probe times out, I know the JVM application itself is actively failing to initialize.
Follow up 3 curveball. You execute the rollback command to restore the previous version, but the pods still fail to start and remain in crash loop backoff. What is your next move?
Answer: if the rollback also fails, it strongly suggests the deployment artifact alone is not the root cause. This points me toward shared dependencies such as Kubernetes secrets, config maps, database availability, certificates, networking, or platform infrastructure that affect both the current and previous versions. I would immediately verify these shared dependencies, review Kubernetes events and cluster health, and engage the platform or infrastructure team while continuing to protect customer traffic.
Production Incident 2. A Spring Boot microservice passes all local tests and boots cleanly on developer laptops. However, immediately upon deployment to Kubernetes production pods, the container exits with code 137 without writing application logs. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this production incident?
Answer: when an application boots locally but fails instantly in production, my priority is to systematically investigate environment drift, C-group memory limits, and missing native dependencies using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify exit codes using kubectl describe pod to distinguish application crashes from kernel kills. 2. Check whether non-production staging environments exhibit the same immediate crash behavior. 3. Review container memory limits against host node resource allocation. Phase 2. Investigation and evidence gathering. 1. Inspect kernel logs on the worker node using DMESG to search for out-of-memory events. 2. Compare JVM heap and C-group memory limits between local Docker runtime and K8's manifests. 3. Verify external configuration profiles. and missing OS-level native binary dependencies. Phase 3. Root cause analysis. 1. Evidence collected. DMESG logs showed memory cgroup out of memory. Killed process Java with exit code 137. 2. Primary root cause. The JVM heap was configured higher than the Kubernetes pod memory limit, causing the Linux kernel killer to terminate the process before logging initiated. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure -XX : plus max RAM percentage equals 75.0 for automatic container awareness, and perform a rolling restart after updating the JVM configuration. 2. Permanent resolution. Update Helm charts to align container memory limits with JVM heap requirements. 3. Validation. Confirm pods are healthy, readiness probes green, and customer transactions executing successfully. Phase 5. Recurrence prevention. 1. Enforce max RAM percentage JVM flags across all base Docker images. 2. Implement container linting tools in CI and CD to block manifests with mismatched memory limits. 3. Standardize staging environment memory constraints to match production bounds. Pro tip interview insight. In containerized environments, avoid configuring fixed JVM heap values without considering Kubernetes memory limits. Using -XX : plus max RAM percentage allows the JVM to size its heap relative to the container's available memory, reducing the risk of kill events.
Follow-up 1 expected. A logical continuation of the incident. What does exit code 137 specifically indicate in Kubernetes, and how does it differ from exit code 1?
Answer. In most Kubernetes environments, exit code 137 indicates the container was forcefully killed by the operating system kernel via sigkill 128 plus signal 9, almost always due to exceeding cgroup memory limits killed. In contrast, exit code 1 means the Java application itself crashed or threw an unhandled runtime exception and voluntarily exited.
Follow-up 2 deeper. Experienced tester. Why did the application fail silently without writing any Java stack trace or error log before crashing?
Answer. When the Linux kernel killer triggers a sigkill signal 9, the process is terminated immediately at the OS level. The JVM is not given time to execute shutdown hooks, flush log buffers, or write heap dumps to disk, leaving application-level log files completely blank.
Follow-up 3 curveball. Suppose memory limits are identical in both environments, but the application still exits with exit code 1 immediately after startup. What would you investigate next?
Answer. I would verify configuration differences such as missing environment variables, incorrect Spring profiles, unavailable databases, expired certificates, missing Kubernetes secrets or config maps, and application startup logs. Exit code 1 usually indicates that the JVM started successfully, but the application failed during initialization because of a configuration or dependency issue.
Production Incident 3. A new version of a Spring Boot microservice is deployed via Jenkins and Kubernetes, successfully creates all pods. However, the liveness and readiness probes fail continuously, keeping the pods out of the load balancer pool and blocking traffic cutover. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this health check failure?
Answer. When a deployment pipeline completes but Kubernetes health checks fail globally, my priority is to isolate probe configuration, port mappings, and application startup bottlenecks using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify pod status with kubectl. Get pods to see if pods are in running state but 0 out of 1 ready. 2. Inspect Kubernetes service endpoints using kubectl. Get endpoints to confirm whether pods have been added to the load balancer. 3. Check monitoring metrics to verify if active user traffic is still being served by legacy pods. Phase 2. Investigation and evidence gathering. 1. Execute kubectl. Describe pod to review Kubernetes events for probe failure reasons and HTTP response codes. 2. Test container health endpoints manually using kubectl exec to run curl against localhost ports. 3. Inspect application property files for port mismatches between Spring Boot server port and K8's container port. 4. Check Spring Boot actuator security rules to confirm if the health endpoint is unauthorized or blocked. Phase 3. Root cause analysis. 1. Evidence collected. Kubectl described pod showed readiness probe failed. HTTP probe failed with status code 401 unauthorized. 2. Primary root cause. A security library update enabled authentication on Spring Boot actuator endpoints by default, causing Kubernetes probe requests to be rejected. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rollback to the previous stable deployment to restore customer traffic. If rollback is not possible, temporarily permit unauthenticated access to /actuator/health until a permanent fix is deployed. 2. Permanent resolution. Update Spring security configuration to explicitly permit unauthenticated access to actuator health endpoints. 3. Validation. Confirm Kubectl get pods shows 1 out of 1 ready. Kubernetes service endpoints include the new pods, and synthetic traffic succeeds. Phase 5. Recurrence prevention. 1. Add automated integration tests in CI and CD that explicitly validate unauthenticated access to health endpoints. 2. Standardize liveness and readiness probe configurations across all Helm chart templates. 3. Implement automated pre-deployment staging health check verification in the pipeline. Pro tip interview insight. Distinguish between liveness and readiness probes. Liveness determines if the container needs a hard restart, while readiness determines if it can receive traffic. Aggressive liveness probes during slow application startup can create unnecessary crash loop backoff failures.
Follow-up 1 expected. A logical continuation of the incident. How do you decide whether to adjust initial delay seconds or increase timeout seconds for health probes?
Answer: I inspect application startup duration logs. If the Spring Boot context requires 45 seconds to initialize database connection pools and cache warmups, initial delay seconds must be set higher than the maximum startup time. Timeout seconds should only be increased if the health endpoint performs heavy internal checks, like database ping operations, that naturally take longer under high CPU load.
Follow-up 2 deeper. Experienced tester. Why is it dangerous for a readiness probe to perform deep dependency checks on external databases or third-party APIs?
Answer: deep readiness probes create cascading cluster outages. If an external database experiences temporary latency, multiple application pods may fail their readiness probes simultaneously, causing Kubernetes to remove all pods from the load balancer endpoints. This turns a localized database slowdown into a total application blackout.
Follow-up 3 curveball. The liveness probe fails and restarts the pod, but during startup the application tries to acquire a database lock that was never released by the crashed instance, deadlocking boot indefinitely. How do you recover?
Answer: I would first stop the restart loop by temporarily increasing the liveness probe thresholds or disabling the liveness probe during recovery. Next, I would identify and safely release the orphan database lock, verify that the application starts successfully, and finally implement automatic lock expiration (TTL) or graceful shutdown logic to prevent stale locks after unexpected pod termination.
Production Incident 4. Following a routine release, new Spring Boot pods start up, but application initialization stalls midway. Logs stop printing without throwing any exceptions, CPU drops to 0%, and the pod remains stuck in 0 out of 1 running indefinitely, blocking traffic cutover. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this startup hang?
Answer: when a Spring Boot application hangs indefinitely during startup without throwing exceptions, my priority is to inspect thread states, connection timeouts, and blocking bean initializations using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify pod status with Kubectl get pods to confirm containers are in running state but stuck at 0 out of 1 ready. 2. Inspect CPU and memory utilization with Kubectl top pods to confirm process activity has dropped to 0. 3. Check application startup logs to identify the exact Spring bean or component where logging halted. Phase 2. Investigation and evidence gathering. 1. Verify whether the JVM process is still responsive by executing jcmd1vm.version or jcmd1vm.uptime. 2. Generate a thread dump from the hanging container using kubectl exec with jcmd1 thread.print. 3. Analyze the main thread state in the dump to locate waiting or timed_waiting states during bean creation. 4. Inspect Spring Bean initialization logic, specifically methods annotated with that post construct. 5. Review database connection pool properties and external HTTP client connection timeout configurations. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed the main thread stuck in waiting inside at post construct method blocked while executing a synchronous external HTTP call through REST template. 2. Primary root cause. A third-party service dependency was offline, and the HTTP client was configured without socket or connection timeouts, causing the Spring context initialization thread to block indefinitely. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform a rolling rollback to the previous stable release using kubectl rollout undo to restore customer traffic immediately. 2. Permanent resolution. Configure explicit connect timeout and read timeout values on all REST template and web client beans, and refactor blocking network calls out of it post construct methods. 3. Validation. Redeploy. Verify that Spring context boots completely within 30 seconds, and confirm pods show 1 out of 1 ready. Phase 5. Recurrence prevention. 1. Enforce mandatory connection and socket timeouts globally across all HTTP client auto configurations. 2. Implement Arch unit static analysis tests in CI and CD pipelines to flag network calls inside at post-construct methods. 3. Move external dependency warmups to asynchronous at event listener with application-ready event.class methods. Pro tip interview insight. Never execute synchronous network or database calls inside Spring at post-construct methods. If an external dependency is slow or down, it blocks the main thread, preventing embedded Tomcat from initializing and causing the pod to hang indefinitely.
Follow-up when expected. A logical continuation of the incident. How do you obtain a thread dump from a Spring Boot container that is hanging during startup before Tomcat or actuator endpoints are active?
Answer. Since the embedded web server is not yet running, actuator endpoints like /actuator/thread dump are unavailable. I execute kubectl exec-it pod name -jcmd1 thread dot print directly inside the running container to send a diagnostic signal to the JVM process PID1 in most containers, dumping all active stack traces directly to the terminal.
Follow-up 2 deeper. Experienced tester. Why does Hikari CP connection pool initialization sometimes cause Spring Boot applications to hang during boot, and how do you fix it?
Answer. If configured with an inappropriate initialization fail timeout value, Hikari CP may wait or repeatedly retry database initialization when the database is unreachable or DNS resolution fails, making application startup appear to hang. I would verify database connectivity, review Hikari CP startup logs, and configure an appropriate initialization failed timeout value so the application fails fast with a clear exception, instead of waiting indefinitely. This allows Kubernetes health probes and deployment pipelines to detect the failure quickly and recover appropriately.
Follow-up 3 curveball. What if the thread dump shows the main thread is in a runnable state, but CPU usage remains at 100% and the application still never completes startup?
Answer. A runnable thread with 100% CPU during startup indicates an infinite loop or heavy CPU execution, such as catastrophic rejects backtracking during configuration parsing, a corrupted cyclic dependency loop in a custom bean post processor, or an infinite loop in a static initializer. I would analyze the thread dump stack trace to pinpoint the exact method and line number executing the loop. If necessary, I would capture a CPU profile using Java Flight Recorder JFR or Async Profiler to identify the hottest execution path.
Production Incident 5. Following a release, a Spring Boot microservice deploys cleanly and logs started application in 2.14 seconds. However, 3 seconds later the Java process exits normally with exit code 0 without throwing any exceptions, causing Kubernetes to enter a restart loop. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this immediate startup exit?
Answer. When a Spring Boot application starts successfully but exits immediately with exit code 0, my priority is to verify web dependency scopes, non-daemon thread persistence, and context shutdown listeners using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect pod details using kubectl. Describe pod to confirm container restart counts and verify exit code 0. 2. Check application logs with kubectl logs to verify if Spring context initialization completed prior to shutdown. 3. Confirm whether the issue affects all newly deployed pods or is isolated to specific environment configurations. Phase 2. Investigation and evidence gathering. 1. Review Spring Boot startup logs for context shutdown triggers like closing annotation config application context. 2. Verify the application's spring.main.web application type configuration to ensure it is not explicitly set to null. 3. Compare dependency build files like pom.xml or build.gradle against the previous working release. 4. Check if Spring Boot starter web dependency scope was accidentally changed to provided or excluded. 5. Inspect command line runner and application runner beans for explicit system.exit or context close calls. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed started application in 2.14 seconds, but no embedded Tomcat initialization messages such as Tomcat started on ports 8080 HTTP. The JVM then exited normally with exit code 0. 2. Primary root cause. A build file refactoring accidentally changed Spring Boot starter web dependency scope to provided, causing the application to start without an embedded web server. As a result, no non-daemon web server threads remained alive, allowing the JVM to exit normally once startup completed. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform a rolling rollback to the previous stable release using kubectl rollout undo to restore active customer traffic immediately. 2. Permanent resolution. Change Spring Boot starter web dependency scope back to compile in pom.xml so embedded Tomcat initializes a persistent web listener thread. 3. Validation. Redeploy, verify startup logs show Tomcat started on ports 8080 HTTP. Confirm pods show 1 out of 1 ready, and verify the container remains running continuously. Phase 5. Recurrence prevention. 1. Add Maven enforcer or Gradle dependency rules in CI and CD to prevent accidental exclusions of core web starters. 2. Implement pipeline staging smoke tests that hit /actuator/health and assert container uptime exceeds 60 seconds. 3. Add automated static code analysis rules to flag explicit system.exit or context close calls in production code. Pro tip interview insight. If a Spring Boot application starts successfully and exits with exit code 0 without errors, verify that an embedded web server is actually being started. Common causes include a missing or incorrectly scoped Spring Boot starter web dependency, spring.main.web application type equals null, or application code that intentionally closes the Spring context.
Follow-up 1 expected. A logical continuation of the incident. How do you distinguish between exit code 0, exit code 1, and exit code 137 when troubleshooting a terminating container?
Answer. Exit code 0 indicates the Java process terminated normally. This may happen because the application completed successfully, the Spring context closed normally, or application code invoked system.exit with 0 after completing its main method, typical of non-web console apps. Exit code 1 indicates an unhandled runtime exception or explicit system.exit with 1. Exit code 137 indicates the OS kernel forcefully terminated the container via sigkill due to exceeding C group memory limits.
Follow-up 2 deeper. Experienced tester. What if Spring Boot starter web is included in the POM, but the application still exits cleanly with exit code 0 right after starting Tomcat?
Answer. This occurs when custom application code explicitly calls configurable application context.close, or a command line runner or application runner bean executes system.exit, or when Spring Cloud task completes its execution and shuts down context. I would inspect all runner beans, event listeners, and custom shutdown hooks for premature exit calls.
Follow-up 3 curveball. When Kubernetes sends SIG-term to a pod during a rolling update, how does Spring Boot handle graceful shutdown, and how do you prevent premature container exit?
Answer: upon receiving SIG term, Spring Boot triggers shutdown hooks, stops accepting new traffic, and waits up to Spring.lifecycle.timeout per shutdown phase for active requests to finish. To prevent premature container termination, termination grace period seconds should be configured longer than Spring Boot's graceful shutdown timeout, so the application has enough time to complete in-flight requests before Kubernetes forcefully terminates the container.
Production Incident 6. A new release of a payment microservice is deployed to Kubernetes. The container fails during initialization, throwing a legal argument exception, could not resolve placeholder and causing pods to enter crash loop back off. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this missing environment variable startup failure?
Answer: when a production application crashes during startup due to an unresolvable property placeholder, my priority is to inspect environment variable injections, Spring configuration profiles, and secret mounts using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify pod crash status using kubectl get pods to confirm pods are in crash loop back off. 2. Check application startup, stack traces via kubectl logs to identify the exact missing property name. 3. Verify if the startup failure affects all production pods or only specific availability zones. Phase 2. Investigation and evidence gathering. 1. Inspect configured environment variables using kubectl describe pod, then verify the runtime environment inside the container using kubectl exec pod name --env. 2. Compare Kubernetes secret and config map manifests in prod against lower environments like dev or staging. 3. Review recent Git commits in application.yml for new at value annotations or at configuration properties classes. 4. Verify whether the missing property is loaded from environment variables, system properties, or external config servers. Phase 3. Root cause analysis. 1. Evidence collected. Application logs showed java.lang.illegal argument exception. Could not resolve placeholder payment _gateway_ API _key and value $curly brace payment _gateway_ API _key close curly brace. 2. Primary root cause. A new payment gateway feature introduced and at value with $curly brace payment _gateway_ API _key close curly brace annotation without a default value, and the corresponding Kubernetes secret manifest was updated in staging, but omitted from the prod release manifest. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Restore the missing payment _gateway_ API _key by deploying the correct Kubernetes secret through Helm or the GitOps pipeline. If immediate recovery is required, temporarily update the production secret and perform a rolling restart. 2. Permanent resolution. Update GitOps infrastructure repositories to ensure secret manifests match application configuration requirements across all environments. 3. Validation. Confirm pods show 1 out of 1 readiness probes succeed and payment gateway health checks pass. Phase 5. Recurrence prevention. 1. Enforce mandatory default fallback values in application.yml or use optional of string for non-critical properties. 2. Implement automated pre-deployment schema validation in CI and CD pipelines to compare Spring Boot property requirements against Kubernetes config maps and secrets. 3. Standardize property binding tests in staging to fail builds if required environment variables are missing. Pro tip interview insight. Provide sensible default values only for non-critical configuration properties in application.yml syntax, such as $curly brace property _name : default _value close curly brace. For mandatory properties, leverage Spring Boots at configuration properties with Jakarta validation annotations. Add not null so context initialization fails fast with a clear validation report, rather than an obscure placeholder exception.
Follow up when expected. A logical continuation of the incident. What is Spring Boot's property resolution order, and why do environment variables override properties defined in application.yml?
Answer: Spring Boot resolves configuration from multiple property sources using a defined precedence order. In a typical Spring Boot deployment, command line arguments take precedence over Java System Properties -D, OS environment variables, and profile-specific application.yml files. OS environment variables intentionally override application.yml values, so external container orchestrators like Kubernetes can inject environment-specific configuration without modifying immutable container images.
Follow up 2 deeper. Experience tester. Why can using default fallback values like $curly brace database underscore URL colon JDBC colon PostgreSQL colon / localhost 5432 / DB close curly brace in application.yml sometimes cause dangerous production failures?
Answer: Fallback values for critical infrastructure properties can mask missing production secrets. If database underscore URL is omitted from the production Kubernetes secret, Spring Boot will silently fall back to the localhost URL, causing the application to fail at runtime with connection refused errors or attempt to connect to an unintended default database. Critical infrastructure properties should never have silent fallbacks. They must fail fast during startup.
Follow up 3 curveball. You verified that the Kubernetes secret object contains the required environment variable, but the application pod still throws could not resolve placeholder after a restart. What causes this?
Answer: This occurs if the secret key name has a subtle case sensitivity mismatch, or if the environment variable in the deployment manifest uses value from .secret keyref pointing to a non-existent key name. Alternatively, it happens if secrets are mounted as files into a volume directory instead of exported as OS environment variables, or if the application expects OS environment variables, while the deployment exposes the secret only as mounted files.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 7. A database connection property change works seamlessly in dev and staging environments. However, immediately after deploying to prod, the Spring Boot application fails to start. Throwing a bind exception during data source configuration. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this dev versus prod configuration failure?
Answer: when configuration changes pass lower environments but fail in prod, my priority is to inspect profile activation, property source precedence, relaxed binding rules, and environment variable overrides using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify active Spring profiles via startup logs to confirm prod profile is loaded. 2. Check pod status using kubectl. Get pods to verify if pods are entering crash loop back off. 3. Determine whether the startup failure affects all production pods or only specific availability zones. Phase 2. Investigation and evidence gathering. 1. Inspect active Spring profiles and loaded property sources using kubectl logs. 2. Compare live environment variables inside the prod container using kubectl exec pod name --env against dev and staging. 3. Review application-prod.yml or Kubernetes config maps for syntax errors, improper YAML indentation, or unescaped characters. 4. Verify Spring Boot relaxed binding mappings between environment variables and at configuration properties classes. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed bind exception. Failed to bind properties under spring.datasource.hikari to com.zaxer.hikari.hikari data source due to an invalid environment variable name in prod. 2. Primary root cause. The prod Kubernetes config map defined an incorrectly named environment variable spring_datasource_hikari_maximum pool size that did not map to Spring Boot's expected property name spring.datasource.hikari.maximum pool size. As a result, the intended configuration was never bound, whereas dev relied on the correctly defined property in application-dev.yml. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Correct the environment variable key in the prod Kubernetes config map to match Spring Boot relaxed binding syntax spring_datasource_hikari_maximum_pool_size and perform a rolling restart. 2. Permanent resolution. Standardize property key definitions across Helm chart templates to enforce uniform environment variable naming in all environments. 3. Validation. Confirm pods show 1 out of 1 ready startup logs show the prod profile loaded cleanly and database pool initialization succeeds. Phase 5. Recurrence prevention. 1. Implement automated property binding tests in CI and CD pipelines to validate at configuration properties against production-like environment variables. 2. Use Spring Boot actuator/config props and /actuator/env in staging to inspect property source origin tracking before releases. 3. Enforce config map schema linting in GitOps deployment pipeline to catch key naming mismatches pre-deployment. Pro tip interview insight. Always follow Spring Boot's relaxed binding rules when injecting configuration via environment variables. Use uppercase with underscores such as spring_datasource_hikari_maximum_pool_size for spring.datasource.hikari.maximum pool size. Never trust manual property overrides without inspecting /actuator/env in a staging environment.
Follow up when expected. A logical continuation of the incident. How does Spring Boot's relaxed binding mechanism translate environment variables like spring_datasource_URL into YAML properties like spring.datasource.url?
Answer. Spring Boot's relaxed binding converts uppercase environment variable names to lowercase dot notation properties. Underscores are converted to dots or dashes, for example. Spring_datasource_URL binds to spring.datasource.url, and spring_datasource_maximum_pool_size binds to spring.datasource.maximum_pool_size. Array indices are represented using underscores, for example. My underscore list underscore 0 underscore binds to my dot list 0.
Follow up 2 deeper. Experience tester. If a property is defined in application.yml, application-prod.yml, a Kubernetes config map, and as a Java system property-d, which value wins in production?
Answer. Java system properties -d take precedence over Kubernetes config maps injected as OS environment variables, which in turn override profile-specific YAML files like application-prod.yml, which override the default application.yml. Understanding this property source precedence is critical for diagnosing why a change in application-prod.yml appears ignored in production.
Follow up 3 curveball. A configuration property change passes startup without throwing bind exception, but customer transactions fail at runtime due to a string-to-duration conversion error. How do you prevent this?
Answer. This occurs when a property expecting a temporal duration like duration.of_seconds with 30 receives a plain integer or string without explicit units in an environment variable override. To prevent this, use Spring Boots at duration unit annotation, for example, at duration unit with chrono unit.seconds, or explicit unit suffixes like 30 seconds or 500 milliseconds in configuration properties, and enforce type validation using Jakarta validation annotations on at configuration properties beans during context startup.
Production Incident 8. During a rolling update of a checkout microservice, incoming user traffic experiences a sudden surge in HTTP 500 internal server errors. Monitoring shows that 50% of customer requests fail, while old and new pods run simultaneously. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this rolling deployment failure?
Answer. When a rolling deployment triggers selective HTTP 500 errors while legacy and new pods coexist, my priority is to isolate API contract mismatches, session serialization errors, and non-backward compatible data models using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify pod distribution using kubectl. Get pods to determine the progress of the rolling deployment. 2. Check load balancer metrics in Grafana to confirm whether HTTP 500 errors originate from legacy pods or newly created pods. 3. Determine if customer transaction failures are isolated to specific API endpoints or session states. Phase 2. Investigation and evidence gathering. 1. Inspect application logs across both legacy and new pods using kubectl logs to capture active stack traces. 2. Examine exception types for JSON deserialization errors, missing property exception, or class cache mismatches. 3. Check shared Redis cache and session stores for serialization conflicts between application versions. 4. Review recent API payload changes and database schema modifications in the new release build. Phase 3. Root cause analysis. 1. Evidence collected. Application logs on legacy pods showed unrecognized property exception while deserializing Redis session objects written by newly deployed pods, indicating that the newer session payload contained fields unknown to the legacy application version. 2. Primary root cause. The new application release introduced a non-backward compatible field, renaming and shared Redis session objects, without maintaining fallback deserialization rules for legacy pods during the rolling update window. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Execute an immediate rollback using kubectl rollout undo to restore a uniform pod fleet and stop active session corruption. 2. Permanent resolution. Apply the expand contract pattern for all shared session models. Configure Jackson at JSON, ignore properties with ignore unknown equals true where appropriate, and introduce version DTOs for Redis session objects to preserve backward compatibility throughout rolling deployments. 3. Validation. Retrigger rolling deployment. Verify HTTP 500 error rates remain at 0% and confirm user checkout flows complete successfully. Phase 5. Recurrence prevention. 1. Implement automated API contract and session schema compatibility tests in CI and CD pipelines. 2. Enforce Jackson backwards compatibility guidelines across all shared data transfer objects. 3. Standardize Canary deployment gates to validate shared cache state before initiating full rolling updates. Pro tip interview insight. During rolling deployments, legacy and new pods run concurrently and share the same database and Redis caches. Always enforce the expand contract pattern for data models and configure Jackson mappers to ignore unknown properties, preventing session deserialization crashes.
Follow up when expected. A logical continuation of the incident. How do you design backward-compatible API changes during rolling deployments using the expand contract pattern?
Answer. The expand contract pattern decouples schema changes into 2 safe releases. In the expand phase, you add new fields while continuing to support and populate legacy fields. Once all pods are updated and reading the new format, you execute the contract phase in a subsequent deployment to safely deprecate and remove old fields without breaking active instances.
Follow up 2 deeper. Experienced tester. Why do Redis session serialization errors frequently occur during rolling deployments, and how do you prevent them?
Answer. They occur when a new version writes modified Java objects to Redis using Java native serialization or strict JSON schemas. When a legacy pod reads that updated session object, deserialization fails due to serial version UID mismatches or missing fields. Prevention involves using version DTOs, JSON serialization configured with ignore unknown, and explicit serial version UID management.
Follow up 3 curveball. What if kubectl rollout undo is executed during a rolling update, but half the pods remain stuck in a terminating state due to graceful shutdown timeouts?
Answer. This happens when in-flight requests or unreleased database connections prevent containers from exiting within Kubernetes termination grace period seconds. I inspect stuck pods using kubectl describe pod, verify application thread states via thread dumps, and if necessary forcefully terminate stuck containers using kubectl delete pod dash grace period equals 0 force to allow clean replacement pods to launch.
Production Incident 9. Following a production deployment, a Java microservice boots successfully and passes basic health checks. However, when users trigger specific business workflows, transactions fail with java.lang. No such method error. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this dependency collision outage?
Answer. When an application boots cleanly but throws no such method error at runtime during specific execution paths, my priority is to isolate class path collisions, transitive dependency overrides, and fat jar packaging defects using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check application error logs using kubectl logs to capture the exact exception class and missing method signature. 2. Determine which specific API endpoints or business transactions trigger the runtime method error. 3. Confirm whether the failure affects all application instances or only specific worker pods. Phase 2. Investigation and evidence gathering. 1. Inspect full exception stack traces to identify the calling class and the target dependency library. 2. Analyze project dependency trees using MVN dependency::tree or Gradle dependencies to locate conflicting transitive libraries. 3. Inspect classpath ordering inside the deployed fat jar artifact using jar-tf to verify which library version was packaged. 4. Review recent build file changes in pom.xml or build.gradle for unpinned or updated third-party library starter versions. Phase 3. Root cause analysis. 1. Evidence collected. Runtime logs show java.lang.no such method error. com.fasterxml.jackson.core.json builder. has name l-boolean. 2. Primary root cause. A newly added third-party SDK transitively pulled Jackson Core 2.11, which overrode the Spring Boot parent managed Jackson Core 2.15 dependency during dependency resolution. The application compiled successfully, but loaded the older library at runtime, resulting in java.lang.no such method error when newer Jackson APIs were invoked. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform an immediate rollback using kubectl rollout undo to restore the previous stable artifact and recover customer transaction processing. 2. Permanent resolution. Exclude the conflicting transitive dependency in pom.xml using explicit exclusions tags and enforce unified version alignment via Maven dependency management. 3. Validation. Rebuild artifact, verify classpath contents, redeploy to staging, execute full regression test suites, and deploy to prod. Phase 5. Recurrence prevention. 1. Integrate Maven Enforcer plugin rules ban duplicate classes and upper bounds into CI and CD pipelines to block builds with classpath conflicts. 2. Standardize bill of materials BOM dependency management across all microservice repositories. 3. Enforce strict dependency version lock files in automated build pipelines. Pro tip interview insight. A no such method error indicates the code compiled against one library version, but loaded a different version from the classpath at runtime. Always configure Maven Enforcer plugin ban duplicate classes in CI and CD pipelines to catch transitive dependency conflicts before packaging production fat jars.
Follow up when expected. A logical continuation of the incident. What is the precise difference between no class def found error and class not found exception in Java?
Answer. Class not found exception is a checked exception thrown at runtime when an application attempts to explicitly load a class using reflection like class dot for name, but the class file is absent from the class path. No class def found error is an error thrown by the JVM when a class was present at compile time, but the JVM fails to find or initialize its definition at runtime, often due to static initializer failures or transitive dependency mismatches.
Follow up deeper. Experienced tester. How do Maven Enforcer rules like upper bounds and ban duplicate classes prevent classpath collisions in CI and CD pipelines?
Answer. The upper bounds rule forces Maven builds to fail if transitive dependencies resolve to different versions across submodules, requiring developers to explicitly declare the highest version in dependency management. The ban duplicate classes rule scans compile scope jars for identical class files coming from different artifacts, preventing runtime classpath shadowing before artifacts reach deployment.
Follow up 3 curveball. What if 2 third-party vendor SDKs strictly require incompatible versions of the same library, such as Jackson 2.11 versus Jackson 2.15, inside the same Spring Boot application?
Answer. When 2 dependencies cannot share a single library version, I isolate one of the libraries using bytecode shading via Maven Shade plugin or Gradle Shadow plugin. Shading relocates class packages, for example, renaming com.fasterxml.jackson to shaded.com.fasterxml.jackson within the compiled artifact, allowing both library versions to coexist safely on the class path without collision.
Production Incident 10. A production deployment fails due to application errors. The team immediately triggers kubectl rollout undo, but the rollback fails because the new database migration added a non-nullable column without a default value, causing legacy pods to crash on startup. As the on-call Java application support engineer, how do you resolve this rollback deadlock?
Answer: when an emergency application rollback fails due to a breaking database schema migration, my priority is to isolate DDL constraints, execute non-destructive database hotfixes, and restore service using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect pod status using kubectl. Get pods to confirm if legacy pods are failing startup health checks post-rollback. 2. Check application startup logs using kubectl logs to capture specific SQL and ORM mapping exceptions. 3. Verify database error rates in Grafana to determine if all application traffic is currently blocked. Phase 2. Investigation and evidence gathering. 1. Review database logs and Flyway or liquid-based migration history tables Flyway_schema_history to identify recent DDL executions. 2. Inspect database table definitions to locate new not null column constraints lacking default values. 3. Review legacy application entity models in V1 code to verify if missing fields trigger insert failures. 4. Verify whether schema changes modified existing column data types or dropped active database columns. Phase 3. Root cause analysis. 1. Evidence collected. Database logs showed PSQL exception. Error. Null value in column status_code violates not null constraint during legacy app insert statements. 2. Primary root cause. The release executed an undecoupled Flyway DDL migration that added a not null column without a default value, breaking backward compatibility with legacy V1 application queries during rollback. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Execute an immediate emergency database patch. Alter table orders. Alter column status_code drop not null to make the column nullable, then re-trigger kubectl rollout undo to restore legacy pods. 2. Permanent resolution. Update Flyway migration scripts to follow non-destructive expand contract principles, applying default values and deferred constraints. 3. Validation. Confirm legacy pods reach 1 out of 1 ready, application queries execute cleanly, and transaction processing stabilizes. Phase 5. Recurrence prevention. 1. Decouple database migrations from application deployments into separate non-destructive pipeline stages. 2. Enforce automated CI and CD Flyway migration checks to block DDL scripts that add not null columns without defaults. 3. Standardize backward compatibility schema testing in staging prior to production deployment. Pro tip: interview insight. Never combine destructive database migrations with application deployments. Always apply schema changes in 3 backward compatible steps. 1. Add nullable column. 2. Deploy app writing to both columns. And 3. Backfill data and apply not null constraint in a subsequent release.
Follow up when expected. A logical continuation of the incident. How do you execute zero downtime database migrations using Flyway or liquid base without breaking active application pods?
Answer: zero downtime migrations require additive, non-destructive DDL. You must never drop columns, rename tables, or add not null constraints without default values in a single step. Database changes are applied first as non-breaking additions. The application is deployed to utilize new columns, and destructive cleanups are deferred to future releases after all legacy code is decommissioned.
Follow up 2 deeper. Experienced tester. Why is rolling back a database migration in production significantly higher risk than rolling back an application deployment?
Answer: application rollbacks simply replace immutable code binaries, whereas database rollbacks alter persistent state. Rolling back DDL that drops columns or tables results in permanent data loss. Furthermore, Down migrations executed while live application pods run can trigger immediate transaction failures and corrupt active dataset states.
Follow-up 3 curveball. What if an emergency application rollback succeeds, but active message queues like Kafka contain unread events serialized in a new schema that legacy pods cannot parse?
Answer: I would immediately pause message queue consumers on the rolled back application to prevent poison pill crash loops. Next, I would deploy an emergency consumer patch or configure schema registry compatibility rules, such as backward or full compatibility, to gracefully ignore unknown fields, or route unparsable messages to a dead letter queue for reprocessing after hotfix deployment.
Production Incident 11. During a blue-green deployment cutover, the ingress router switches 100% of live traffic to the green environment. Immediately, customers experience HTTP 502 bad gateway errors and duplicate transaction charges. As the on-call Java application support engineer, how do you resolve this blue-green cutover outage?
Answer: when a blue-green deployment switch causes HTTP 502 errors and duplicate processing, my priority is to inspect router target group health, session stickiness, and background worker concurrency using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check ingress router metrics in Grafana to verify traffic distribution between blue and green target groups. 2. Inspect green pod status using kubectl. Get pods to check if target pods are unready or failing health probes. 3. Determine if customer transaction failures are caused by routing drops or backend database locking. Phase 2. Investigation and evidence gathering. 1. Inspect ingress controller and AWS ALB target group health logs to verify if green pods passed readiness gates. 2. Examine database connection pool metrics to check if blue and green environments simultaneously exhausted database limits. 3. Check active message queue consumer groups Kafka or RabbitMQ to verify if background workers were processing concurrently on both blue and green clusters. 4. Review session store configurations for missing sticky session rules or cross-environment token validation failures. Phase 3. Root cause analysis. 1. Evidence collected. Database connection logs showed too many connections and duplicate key violations in order processing tables. 2. Primary root cause. The blue-green cutover successfully redirected customer HTTP traffic to the green environment, but background Kafka consumers and Quartz schedulers continued running on both blue and green. As both environments processed the same messages concurrently, duplicate business transactions occurred and database connection pools became exhausted. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Immediately revert ingress router traffic back to the stable blue environment and pause active background consumers on the green cluster. 2. Permanent resolution. Decouple background message consumers from web traffic cutovers and implement automated consumer pause scripts during blue-green transitions. 3. Validation. Confirm ingress traffic routes 100% cleanly to blue, verify 0% HTTP 502 errors, and validate single consumer processing. Phase 5. Recurrence prevention. 1. Isolate background event consumers and Quartz batch schedulers into dedicated deployment groups separate from HTTP web tiers. 2. Recalculate database connection pool allocations to ensure database capacity supports dual-stack blue-green deployments. 3. Implement automated pre-cutover validation gates in CI and CD to verify background consumer state before switching HTTP routers. Pro tip: interview insight. In blue-green deployments, switching the HTTP ingress router only redirects web traffic. Background message consumers Kafka or JMS and Quartz scheduled jobs on the blue stack remain active unless explicitly paused, leading to race conditions, duplicate processing, and database pool exhaustion.
Follow up when expected. A logical continuation of the incident. How do you manage session persistence and WebSocket connections during a blue-green deployment cutover?
Answer: for HTTP sessions, session state must be offloaded to a shared external Redis cluster, so users remain authenticated regardless of which environment receives the request. For long-lived WebSocket connections, Cutovers require graceful connection draining, instructing client SDKs to reconnect so they naturally establish new WebSocket channels on the green target group.
Follow up 2 deeper. Experienced tester. Why must database connection pool limits be carefully re-evaluated before executing blue-green deployments?
Answer: during blue-green cutovers, both blue and green application stacks run concurrently. If each stack allocates a maximum pool size of 50 connections across 20 pods, total potential connections double from 1,000 to 2,000. If the primary database max_connections limit is 1,500, the database will reject connections, causing HTTP 500 errors across both stacks.
Follow up 3 curveball. What if the blue-green router cutover succeeds, but client-side DNS caching causes 15% of users to continue sending requests to the blue environment for hours after cutover?
Answer: this occurs when downstream client DNS resolvers ignore low TTL values. To prevent outage during blue decommissioning, keep the blue environment running in a read-only proxy mode, forwarding incoming HTTP requests to the green target group until DNS propagation reaches 100% and blue ingress traffic drops to 0.
Production Incident 12. A canary release routes 5% of live production traffic to a new microservice version. While staging tests past 100%, canary pods show a sharp spike in HTTP 500 errors and thread contention under real customer traffic. As the on-call Java application support engineer, how do you resolve this canary deployment failure?
Answer: when a canary release exposes production-only thread contention or error spikes, my priority is to analyze telemetry metrics, trigger automated canary aborts, and isolate concurrency bottlenecks using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Compare Grafana APM metrics between canary pods 5% traffic and baseline pods 95% traffic. 2. Verify if customer error spikes are contained within the canary pod subset or impacting overall SLA thresholds. 3. Check canary deployment status in Argo rollouts or Istio service mesh controllers. Phase 2. Investigation and evidence gathering. 1. Inspect canary application logs using kubectl logs to identify runtime exceptions and thread lock contention. 2. Capture thread dumps from canary pods using JCMD onethread.print to locate blocked thread states under live traffic. 3. Review database query metrics to verify if unindexed database queries executed by canary pods triggered connection starvation. 4. Compare JVM heap utilization and garbage collection pause times between canary and baseline pods. Phase 3. Root cause analysis. 1. Evidence collected. Thread dumps on canary pods revealed 40 worker threads in blocked state waiting on a synchronized singleton cache wrapper. 2. Primary root cause. A new synchronized method introduced in the release created severe thread contention under live concurrent production traffic that could not be replicated during low concurrency staging tests. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Immediately abort the canary deployment using Argo rollouts abort or Istio traffic shifting, instantly setting canary traffic to 0% and routing 100% traffic to baseline pods. 2. Permanent resolution. Refactor the synchronized bottleneck using concurrent hash map or non-blocking atomic references and redeploy to staging. 3. Validation. Confirm 0% traffic reaches canary pods, baseline HTTP error rates return to 0%, and transaction latencies normalize. Phase 5. Recurrence prevention. 1. Configure automated Prometheus analysis templates in Argo rollouts to automatically abort canary deployments if error rates exceed 0.5%. 2. Integrate automated load and concurrency testing using JMeter or Gatling into pre-production CI and CD pipelines. 3. Standardize thread contention profiling using a sync profiler during staging stress tests. Pro tip interview insight. Canary deployments are designed to catch hidden production bugs before widespread impact. Always pair canary deployments with automated metric analysis rules in Argo rollouts or Istio so the rollout aborts automatically when error or latency thresholds are breached.
Follow up when expected. A logical continuation of the incident. How do Argo rollouts and service mesh controllers split traffic precisely between baseline and canary pods?
Answer. Argo rollouts interacts with ingress controllers or service meshes like Istio or AWS App Mesh. Instead of relying solely on pod replica ratios, Istio manipulates virtual service routing rules to direct an exact percentage, such as 5% of HTTP header traffic to the canary subset, while 95% continues to baseline pods.
Follow up two deeper. Experienced tester. What key golden signals should trigger an automated canary deployment abort?
Answer. An automated abort should trigger on the 4 golden signals. Error rate HTTP 500 level spikes, latency P99 response time degradation, saturation CPU, memory, or connection pool exhaustion, and traffic unexpected drops in transaction throughput compared to baseline pods.
Follow up three curveball. What if a canary deployment appears 100% healthy during a 30-minute metric evaluation window, but introduces a slow memory leak that crashes pods 4 hours after full 100% rollout?
Answer. This highlights the limitation of short canary windows for slow memory leaks. I would trigger an immediate rolling rollback to the previous stable release. To prevent recurrence, implement automated soak testing in staging environments and configure a PM Heap trend, alerts monitoring GC memory recovery after full GC to detect memory leaks before production releases.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 13. During a production release, a Flyway database migration script executes an alter table statement on a 50 million row orders table. The migration acquires an exclusive lock, blocking all application queries and bringing down the entire microservice architecture. As the on-call Java application support engineer, how do you resolve this database lock outage?
Answer: when an automated database migration acquires an exclusive table lock during a production release, my priority is to identify the blocking process, terminate the DDL lock safely, and restore application query flow using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check database, APM and connection pool, dashboards in Grafana to confirm rising active query locks and connection starvation. 2. Verify application error logs using kubectl logs to identify database connection timeout exceptions. 3. Confirm if transaction failures impact the entire application architecture or specific database schemas. Phase 2. Investigation and evidence gathering. 1. Query active database lock tables such as pg_stat_activity in Postgres SQL or show process list in MySQL to locate the blocking DDL process ID. 2. Identify the specific Flyway or liquid-based migration script executing the blocking alter table statement. 3. Examine query lock dependency trees to confirm that incoming application select and insert queries are queued behind the DDL lock. 4. Review database connection pool usage to verify if all application worker threads are blocked waiting for database connections. Phase 3. Root cause analysis. 1. Evidence collected. Postgres SQL pg_stat_activity showed a Flyway process executing alter table orders, add column status varchar, with 20 default new holding an access exclusive lock. 2. Primary root cause. The Flyway migration executed an alter table operation that required an access exclusive lock on a 50 million row production table during peak traffic hours. Without a configured lock timeout, incoming application queries targeting that table became blocked behind the migration, leading to widespread request timeouts and service degradation. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Terminate the blocking DDL migration query immediately using pg_terminate_backend with PID in Postgres SQL or kill PID in MySQL. Abort the deployment pipeline and restore application database connectivity. 2. Permanent resolution. Rewrite the migration script using non-blocking DDL, adding nullable columns without defaults or creating indexes concurrently and execute during off-peak hours. 3. Validation. Confirm active database locks clear, database connection pools normalize, and application transaction throughput recovers. Phase 5. Recurrence prevention. 1. Mandate strict lock timeout. Set lock_timeout equals 5 seconds in all flyway and liquid-based migration scripts to fail fast if locks cannot be acquired. 2. Enforce static DDL schema reviews using tools like PG schema diff in CI and CD pipelines to flag dangerous table rewrites. 3. Execute online schema changes for large MySQL production tables using proven online migration tools such as GHOST or PT Online Schema Change, and use database native online DDL features such as create index concurrently in PostgreSQL whenever supported to minimize locking and service disruption. Pro tip interview insight. Never execute unthrottled DDL migrations on large production tables during peak traffic. Always configure lock_timeout in flyway scripts so migrations fail fast if a lock cannot be acquired within 5 seconds, preventing global application lockups.
Follow up when expected. A logical continuation of the incident. How do you create database indexes on large, high-traffic production tables without locking write operations?
Answer: in PostgreSQL, use create index concurrently, which builds the index without acquiring an access-exclusive lock, allowing concurrent inserts and updates to continue. In MySQL, use in NoDB online DDL algorithm equals in place, lock equals null or tools like GHOST to avoid table locking.
Follow up deeper. Experienced tester. What happens when a flyway migration fails midway through execution, leaving the flyway_schema_history table in a corrupted state?
Answer: when a non-transactional DDL migration fails midway, flyway marks the script as failed success equals false in flyway_schema_history and blocks subsequent deployments. To recover, you must manually repair the database state, fix the DDL script, and run flyway repair to clean the failed schema history entry before redeploying.
Follow up 3 curveball. How do online schema change tools like GHOST or PT Online Schema Change perform zero downtime alter table migrations on multi-terabyte tables?
Answer: online schema change tools create a ghost copy of the target table, apply the DDL modification to the ghost table, and stream live binary log events binlog or trigger-based updates to keep the ghost table synchronized. Once fully caught up, a swift atomic table swap is executed in milliseconds, avoiding table locks.
Production Incident 14. During a scheduled production release window, CI and CD deployment pipelines fail abruptly during image build and container startup phases. Logs show connection timeouts downloading dependencies from the private Nexus artifact repository. As the on-call Java application support engineer, how do you resolve this artifact repository deployment failure?
Answer: when an artifact repository timeout halts production deployment pipelines, my priority is to inspect repository health, bypass remote dependency fetches using local caches, and adjust HTTP socket timeouts using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect CI and CD pipeline. Build logs in Jenkins or GitLab to identify specific artifact download failure points. 2. Check private Nexus or Artifactory repository health dashboards to determine if latency is global or regional. 3. Verify whether ongoing production deployments can be paused or reverted to avoid partial rollout states. Phase 2. Investigation and evidence gathering. 1. Review pipeline error traces for java.net.socket timeout exception or 504 gateway timeout from Nexus endpoints. 2. Test network latency and throughput from CI and CD runner nodes to the artifact repository using curl and NC. 3. Inspect build configuration files like pom.xml or build.gradle for missing repository mirror failovers or aggressive HTTP timeouts. 4. Check whether runner nodes utilize persistent local dependency caches or execute clean uncached builds on every run. Phase 3. Root cause analysis. 1. Evidence collected. Pipeline logs showed socket timeout exception. Read timed out after 30,000 milliseconds while downloading core Spring Boot jar dependencies from Nexus. 2. Primary root cause. Multiple parallel production build runners overwhelmed a single Nexus repository node during a synchronized release window, exceeding default 30-second HTTP socket timeouts on uncached build runners. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Redirect CI and CD pipeline runners to a secondary nexus or artifactory mirror repository, or switch builds to runners with pre-populated dependency caches so production deployments can continue while the primary repository is restored. 2. Permanent resolution. Configure HTTP retry handlers and extend socket read timeouts in Maven settings.xml using maven.wagon.rto properties. 3. Validation. Re-trigger deployment pipeline, confirm 100% artifact download success, and verify successful container startup. Phase 5. Recurrence prevention. 1. Implement persistent local dependency caching such as build kit cache mounts on all CI and CD pipeline runner nodes. 2. Configure high availability active nexus repository clusters behind a load balancer. 3. Enforce pre-release artifact prefetching in staging environments before opening production deployment windows. Pro tip interview insight. Never rely on uncached network fetches from central artifact repositories during critical production deployment windows. Always configure CI and CD build runners with persistent local dependency caching and secondary repository mirrors, so builds succeed even during repository latency.
Follow-up 1 expected. A logical continuation of the incident. How do you configure Maven build tools with retry handlers and extended socket timeouts to handle transient repository network blips?
Answer: in Maven settings.xml, you configure Wagon HTTP provider properties like maven.wagon.rto read timeout and maven.wagon.http.retryhandler.count. Setting retry counts to 3 and socket read timeouts to 120 seconds instructs Maven to automatically retry failed artifact downloads over transient network blips without crashing the pipeline.
Follow-up 2 deeper. Experience tester. Why should production Docker files use multi-stage builds and local registry caching to insulate deployments from artifact repository downtime?
Answer: multi-stage Docker files separate dependency compilation from final image packaging. By caching the dependency resolution layer separately from application source code, Docker only re-downloads jar dependencies when build files change. This minimizes network traffic to Nexus and ensures cached builds complete even during repository outages.
Follow-up 3 curveball. What if Nexus goes offline completely during an emergency production hotfix deployment and no local cache exists on the build runner?
Answer: if Nexus is completely unavailable and no dependency cache exists, I would first determine whether an identical artifact was successfully built earlier in the release pipeline and promote that immutable artifact instead of rebuilding. If rebuilding is absolutely required, I would temporarily configure Maven to use a synchronized disaster recovery repository or internal mirror. Manually copying jars into Docker images would be an absolute last resort, because it breaks build reproducibility and artifact traceability.
Production Incident 15. A Java microservice deployed in a Docker container on Kubernetes experiences severe performance degradation and sudden OS kills with exit code 137. Investigation reveals the Dockerfile hard-coded JVM heap flags -xmx2g while container limits were set to 1 GB. As the on-call Java application support engineer, how do you resolve this container JVM misconfiguration?
Answer: when a hard-coded JVM configuration conflicts with Kubernetes container memory limits causing process termination, my priority is to analyze cgroup memory bounds, enable dynamic JVM container awareness, and align memory ratios using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify container termination reasons using kubectl, describe pod to confirm killed state and exit code 137. 2. Compare Kubernetes container memory limits.memory in deployment manifests against underlying node host capacity. 3. Check Grafana metrics for JVM heap usage, metaspace growth, and container working set memory trends prior to the crash. Phase 2. Investigation and evidence gathering. 1. Inspect the application Docker file and entry point scripts for hard-coded JVM memory flags like -xmx or -xms. 2. Verify active JVM configuration flags inside running containers using kubectl exec with jcmd1vm.flags. 3. Inspect Kubernetes events and container termination messages first to confirm killed status. Then review worker node message logs if deeper kernel-level confirmation of the Linux killer decision is required. 4. Inspect off-heap memory components including metaspace, thread stacks, and direct byte buffers. Phase 3. Root cause analysis. 1. Evidence collected. Message logs showed memory cgroup out of memory. Killed process Java, while JCMD showed -xmx2g configured inside a container with a 1 GB limit. 2. Primary root cause. The Docker file contained hard-coded -xmx2g legacy flags, causing the JVM to allocate heap beyond the container's 1 GB cgroup memory ceiling and triggering Linux kernel kill termination. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Update container environment variables or deployment manifest to inject -xx:\max RAM percentage equals 75.0 and remove hard-coded -xmx flags, then trigger a rolling restart. 2. Permanent resolution. Rebuild base Docker images to utilize dynamic container awareness flags -xx:+. Use container support -xx:\max RAM percentage equals 75.0 without fixed heap sizing. 3. Validation. Confirm pods show 1 out of 1 ready. Verify jcmd1vm.flags calculates heap dynamically relative to container limits and monitor stability under load. Phase 5. Recurrence prevention. 1. Enforce standardized base Docker images with dynamic container RAM percentage configuration across all microservices. 2. Implement CI and CD Dockerfile linter checks such as hadlint to block images containing static -xmx or -xms flags. 3. Configure Kubernetes pod limit ranges and request ratios to ensure consistent memory allocations across environments. Pro tip interview insight. Modern JVMs Java 11+ are container aware. Never hardcode fixed -xmx flags in Docker files. Always use -xx:\max RAM percentage equals 75.0 so the JVM automatically scales its heap based on the Kubernetes container memory limit, leaving 25% for metaspace, thread stacks, and off-heap memory.
Follow-up when expected. A logical continuation of the incident. What is the difference between JVM heap memory and off-heap native memory, and why can a container be killed even if heap usage is low?
Answer. JVM heap stores instantiated Java objects managed by garbage collection. Off-heap native memory includes metaspace, thread stacks, direct byte buffers, JIT code cache, and internal GC data structures allocated directly from OS memory. If off-heap allocations grow unchecked, total process memory exceeds the container cgroup limit, causing the Linux kernel to kill the container, even if heap usage is under 50%.
Follow-up 2 deeper. Experience tester. How does -xx:\max RAM percentage differ from -xmx, and how do you calculate total container memory bounds to prevent cgroup kills?
Answer. -xmx sets a static maximum heap size in megabytes or gigabytes regardless of container size. -xx:\max RAM percentage calculates max heap dynamically as a percentage of the container's cgroup memory limit. For example, 75% of 2 GB equals 1.5 GB heap. The remaining 25% buffer accommodates off-heap requirements like metaspace, thread stacks, and OS overhead.
Follow-up 3 curveball. What if a Java 17 container is configured with -xx:\max RAM percentage equals 75.0, but still gets killed due to high metaspace growth after dynamic class loading?
Answer. This occurs when dynamic class generation such as heavy reflection or proxy creation exhausts native memory. By default, metaspace has no maximum cap. -xx:\max metaspace size is unlimited. To prevent cgroup kills, explicitly cap metaspace using -xx:\max metaspace size equals 256 megabytes so the JVM throws an explicit out-of-memory error, metaspace that triggers a clean Java stack trace, rather than an undiagnostic OS kernel kill.
Production Incident 16. During a rolling deployment of 20 microservices, Spring Cloud Config Server experiences a brief network glitch. Bootstrap initialization fails across all launching pods, with Config Server instance unavailable exception, entering a global crash loop backoff cascade. As the on-call Java application support engineer, how do you resolve this Config Server deployment outage?
Answer: when centralized config server unavailability triggers a cascading application startup crash, my priority is to restore config server health, enable client-side retry mechanisms with exponential backoff, and stabilize Bootstrap initialization using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect pod crash statuses across all microservices using kubectl. Get pods to verify the extent of crash loop backoff states. 2. Check application startup logs with kubectl logs to confirm unresolvable config server connection exceptions. 3. Verify Spring Cloud config server health endpoints and backing Git repository connectivity in Grafana. Phase 2. Investigation and evidence gathering. 1. Review Bootstrap logs for org.springframework.web.client.resource access exception. I/O error on GET request for config server. 2. Inspect microservice bootstrap.yml files for spring.cloud.config.failfast and spring.cloud.config.retry property settings. 3. Test direct HTTP connectivity and response latency from worker pods to config server endpoints using kubectl exec with curl. 4. Verify whether Spring Retry, and Spring Boot Starter AOP dependencies are present on client class paths. Phase 3. Root cause analysis. 1. Evidence collected. Bootstrap logs showed config server instance unavailable exception, immediately followed by context initialization crash without retrying. 2. Primary root cause. Microservices configured spring.cloud.config.fail fast equals true but omitted Spring Retry dependencies, causing pods to crash instantly during a transient 5-second config server network glitch during deployment. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Restart config server instances, scale config server replicas to handle boot traffic, and perform a rolling restart of affected microservice pods. 2. Permanent resolution. Add Spring Retry and Spring Boot Starter AOP dependencies to client microservices and configure exponential backoff retry parameters. 3. Validation. Confirm pods show 1 out of 1 ready, verify configuration properties fetched successfully during boot, and validate service health. Phase 5. Recurrence prevention. 1. Configure Spring Cloud config client retry policies, enable high availability for config server instances, and use cached local configuration only where business continuity requirements permit, while monitoring for configuration drift. 2. Deploy Spring Cloud config server in a high availability multi-replica configuration behind a load balancer. 3. Enforce mandatory Spring Retry configuration standards across all microservice archetype templates. Pro tip interview insight. When using centralized Spring Cloud config servers, always combine spring.cloud.config.fail fast equals true with Spring Retry and Spring Boot Starter AOP. This forces microservices to retry connection attempts with exponential backoff during transient network glitches, rather than crashing instantly.
Follow up when expected. A logical continuation of the incident. How do spring.cloud.config.failfast and spring.cloud.config.retry work together during application bootstrapping?
Answer: fail fast equals true instructs Spring Boot to halt context startup immediately if config server is unreachable, preventing the app from booting with partial or missing properties. When Spring Retry is added, Spring Boot intercepts that startup failure and retries fetching configuration up to max attempts with exponential backoff before throwing a fatal exception.
Follow up 2 deeper. Experienced tester. What are the operational risks of enabling client-side configuration property caching in Spring Cloud config server client applications?
Answer: Client-side caching allows microservices to boot using locally cached properties if config server is down. However, the risk is configuration drift. If properties are updated in Git while config server is offline, microservices will boot using stale cached configuration, leading to inconsistent runtime behavior across pods.
Follow up 3 curveball. What if the config server is online, but a Git repository backend timeout causes config server to return HTTP 500 errors to bootstrapping microservices?
Answer: I would inspect config server logs to confirm Git backend latency or fetch failures. To reduce dependency on live Git access during startup, I would enable local Git repository cloning using the appropriate Spring Cloud config Git settings, keep repositories synchronized in advance, and deploy multiple config server instances behind a load balancer so transient Git backend delays do not interrupt client configuration requests.
Production Incident 17. A feature flag is toggled on and launched darkly to enable a new payment gateway flow in live production without deploying new code. Immediately, customer checkout requests fail with null pointer exception and thread pool exhaustion. As the on-call Java application support engineer, how do you resolve this feature flag outage?
Answer: when a production feature flag toggle triggers immediate runtime crashes, my priority is to execute the feature flag kill switch to restore traffic, investigate uninitialized dependency states, and refactor fallback logic using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Correlate APM error spikes in Grafana or Datadog with the exact timestamp of the launch darkly feature flag toggle. 2. Check application logs using kubectl logs to capture the specific runtime exceptions triggered by the toggled code path. 3. Confirm whether request failures impact 100% of checkout traffic or only specific user segments targeted by the flag. Phase 2. Investigation and evidence gathering. 1. Review stack traces for java.lang.null pointer exception or unhandled Spring Bean lookup failures in flagged code paths. 2. Inspect feature flag evaluation logic to verify whether Spring Beans or configuration properties behind the flag were initialized at startup. 3. Check thread pool metrics in APM dashboards to verify if blocked threads in the new feature path caused thread pool exhaustion. 4. Review launch darkly audit logs to confirm flag rule modifications and targeted environment variations. Phase 3. Root cause analysis. 1. Evidence collected. Runtime logs showed null pointer exception inside new payment gateway service process when accessing an unconfigured client bean. 2. Primary root cause. The feature flagged code assumed a required payment gateway client bean was initialized at boot, but the bean was conditionally disabled via at conditional on property when the JVM originally booted with the flag off. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Instantly toggle the feature flag back to off in the launch darkly control panel to kill the feature path and restore customer checkout traffic immediately without code rollbacks. 2. Permanent resolution. Refactor code behind feature flags to initialize required beans safely at startup or handle null states defensively with fallback providers. 3. Validation. Confirm 0% null pointer exception errors, verify thread pool utilization returns to normal, and validate transaction success. Phase 5. Recurrence prevention. 1. Mandate automated feature flag contract testing in CI and CD pipelines, testing code paths explicitly in both on and off states. 2. Enforce defensive coding guidelines requiring default fallback execution paths for all feature flag toggles. 3. Implement automated feature flag lifecycle tracking to clean up stale feature flags and reduce code debt. Pro tip interview insight. Feature flags decouple deployment from feature exposure, providing an instant kill switch in production. However, code behind feature flags must always handle null states defensively and never rely on Spring Beans that were conditionally disabled when the JVM booted with the flag off.
Follow-up when expected. A logical continuation of the incident. How do you unit test and integration test feature flagged code paths to ensure zero runtime failures whether a flag is on or off?
Answer: in unit tests, Mock the feature flag evaluation client such as launch darkly LD client to explicitly test both true and false evaluation branches. In integration tests, execute test suites under both flag states to verify that Spring context initialization, bean auto-wiring, and fallback logic function perfectly regardless of flag status.
Follow up 2 deeper. Experienced tester. What are the operational dangers of feature flag debt in large enterprise Java codebases?
Answer: feature flag debt occurs when old feature flags are left in code after rollout. It increases cyclomatic complexity, creates dead code paths, complicates testing, and introduces risk where an accidental toggle of a stale flag in production invokes obsolete or unmaintained business logic, causing unexpected outages.
Follow up 3 curveball. What if toggling a feature flag off fails to restore production health because the SDK cached the on state locally in memory and lost connection to the feature flag management server?
Answer: if local SDK and memory caching prevents flag updates due to network disconnects, I would execute a rolling pod restart kubectl rollout restart to force containers to reinitialize and fetch fresh flag configurations. To prevent this, configure local SDK connection timeouts and fallback flag evaluation defaults in application code.
Production Incident 18. A production release of a reporting microservice deploys cleanly, pods show 1 out of 1 ready, and HTTP APIs respond normally. However, 24 hours later, stakeholders report that automated daily batch reports and email notifications silently stopped executing. As the on-call Java application support engineer, how do you resolve this scheduled job failure?
Answer: when automated background scheduled jobs silently stop executing post-deployment, my priority is to inspect Spring scheduling annotations, shed lock database lock states, and thread pool execution bottlenecks using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Review application logs using kubectl logs to verify whether its scheduled method invocation logs stopped appearing post-deployment. 2. Inspect shedlock or quartz database lock tables shedlock or QRTZ_locks to check if active locks are stuck in a locked state. 3. Confirm whether API endpoints on the same microservice remain functional while background batch jobs are stalled. Phase 2. Investigation and evidence gathering. 1. Inspect Spring configuration classes to verify whether an enable scheduling annotation was accidentally removed during code refactoring. 2. Examine shedlock database table entries for stale lock rows where locked underscore at timestamps indicate locks were never released by terminated pods. 3. Generate a thread dump using JCMD1 thread. Print a check if Spring's default single-threaded task scheduler is blocked by a stuck job. 4. Check recent git commit diffs for modifications to cron expressions, time zones, or shed lock at most for parameters. Phase 3. Root cause analysis. 1. Evidence collected. Shedlock database query showed locked underscore by equals pod v1 abc with lock underscore until set to 24 hours in the future after pod v1 was abruptly killed during rolling update. 2. Primary root cause. Shedlock was configured with an excessively high lock at most for equals 24 hours parameter without lock release on shutdown hooks, causing an orphan database lock to block all newly deployed pods from executing the scheduled job. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. After confirming that no active scheduler instance still owns the lock, safely remove or update the stale shed lock record so another healthy application instance can immediately acquire the lock and resume scheduled job execution. 2. Permanent resolution. Reduce shed lock at most to a realistic maximum execution duration such as 30 minutes and configure Spring Boot graceful shutdown hooks to release locks on SIG term. 3. Validation. Confirm scheduled task logs execute cleanly, verify batch emails deliver, and monitor shed lock acquisition cycles. Phase 5. Recurrence prevention. 1. Implement automated integration tests asserting at scheduled bean registration and shed lock release behavior. 2. Configure Prometheus or Grafana alerts to trigger if expected scheduled job execution metrics do not increment within defined cron intervals. 3. Enforce mandatory multi-threaded task scheduler configuration, thread pool task scheduler, across all scheduled microservices. Pro tip interview insight. In multi-pod Kubernetes clusters, background scheduled jobs at scheduled use shed lock to prevent duplicate runs. Always configure lock at most for slightly longer than the maximum expected execution time of the scheduled job. This ensures stale locks expire automatically after abnormal pod termination, while avoiding duplicate executions during normal long-running jobs.
Follow up when expected. A logical continuation of the incident. How does Shedlock prevent duplicate execution of Spring at scheduled tasks across multiple Kubernetes pod replicas?
Answer: Shedlock uses a shared database table or RIDI's key to acquire an exclusive distributed lock before executing a scheduler lock annotated method. Whichever pod successfully inserts or updates the lock row first executes the task, while all other pod replicas skip execution during that interval, ensuring exactly once execution across the cluster.
Follow up 2 deeper. Experienced tester. What is the difference between lock at most for and lock at least for parameters in Shedlock, and why are both important?
Answer: Lock at most for specifies the maximum duration a lock is held if the executing node dies or hangs, acting as a safety net against stale locks. Lock at least for specifies the minimum duration a lock must be held, preventing duplicate executions across nodes if task execution time is shorter than clock drift variations between cluster nodes.
Follow up 3 curveball. What if a Spring at scheduled task uses Spring's default single-threaded task scheduler, and a long-running or stuck job blocks all other scheduled tasks in the same instance?
Answer: By default, Spring Boot configures a single-threaded thread pool task scheduler. If one scheduled task hangs on an untimed I/O call, no other scheduled methods in that application instance will ever execute. To prevent this, configure a custom thread pool task scheduler bean with a pool size greater than 1. For example, pool size equals 5 in a configuration class.
Category 1 conclusion.
Mastering application startup, configuration management, and deployment strategies is what protects the modern enterprise from critical post-release outages, environment drift, and service disruptions. By establishing automated secret validation gates, enforcing non-destructive database migrations, and implementing backward-compatible expand contract data patterns, you build a resilient, self-healing deployment ecosystem.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire master vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition from Category 1 deployment pipelines to Category 2 JVM runtime.
While mastering deployment pipelines and startup initializations is essential, you cannot maintain service availability if the underlying runtime process fails. Thread locks, heap memory exhaustion, and garbage collection latency are the baseline operational threats to any running service. We now transition from deployment and pipeline layers to the core runtime engine of the platform. Category 2, JVM, Heap, GC, and Java platform.
Category 2, JVM, Heap, GC, and Java platform.
JVM, Heap, garbage collection, and Java platform production incidents govern how application memory, thread execution, and platform upgrades are managed and optimized across enterprise microservices. This category deep dives into resolving continuous heap memory growth, analyzing native memory crashes, tuning G1GC latency spikes, diagnosing metaspace leaks, analyzing HS_error_PID JVM crash dumps, and utilizing Java flight recorder profiling. Mastering these scenarios ensures you can deliver a highly performant, resilient Java runtime ecosystem.
Category 2, JVM, Heap, GC, and Java platform 19 to 36.
Here are the 18 JVM, memory runtime and platform runtime incidents we will solve in this category. Incident 19. Java heap memory continuously grows until out-of-memory error occurs. Incident 20. Frequent full GC pauses disrupt application request processing. Incident 21. G1GC latency spikes degrade application response times under load. Incident 22. Native memory exhaustion crashes container despite available heap. Incident 23. Metaspace exhaustion triggers context initialization failure. Incident 24. Collection-based memory leak retains unclosed Java objects. Incident 25. Heap dump analysis identifies unexpected retained object roots. Incident 26. Direct byte buffer memory exhaustion causes JVM process crash. Incident 27. Incorrect JVM tuning degrades overall application throughput. Incident 28. Large object allocations trigger severe garbage collection storms. Incident 29. Finalizer, soft reference, or phantom reference misuse delays memory cleanup. Incident 30. No class def found error versus class not found exception troubleshooting. Incident 31. Java 17 or 21 jigsaw module reflection access restrictions. Incident 32. JAXB package removed after Java platform upgrade. Incident 33. Compressed OOPS disabled causing unexpected memory footprint increase. Incident 34. Code cache exhaustion degrades JIT compilation performance. Incident 35. JVM crash HS_error_PID log file analysis and investigation. Incident 36. Java Flight Recorder JFR profiling and thread investigation. Total 18 JVM, memory runtime and platform runtime incidents. Let's dive into Incident 19.
Production Incident 19. Over a 48-hour period post-release, an order processing microservice shows a steady stair-step increase in heap memory usage. Garbage collection cycles recover progressively less memory until pods throw java.lang. Out of memory error. Java heap space and crash. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this heap memory leak?
Answer: when an application exhibits continuous heap growth leading to out-of-memory error, my priority is to generate a heap dump, analyze dominator trees to identify retained object roots, and replace unbounded caches using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Grafana APM heap metrics to confirm the characteristic stair-step memory pattern, where post-GC baselines rise over time. 2. Check pod restart counts using kubectl. Get pods to verify if all order processing instances or specific worker pods are crashing. 3. Determine whether customer transaction processing is completely halted or experiencing severe latency degradation. Phase 2. Investigation and evidence gathering. 1. Retrieve automatically generated heap dump files. .hprof triggered by JVM flag -xx : plus heap dump on out-of-memory error. 2. Load the heap dump into Eclipse MAT memory analyzer tool and run the dominator tree and leak suspects report. 3. Trace incoming strong references from GC roots to identify the exact class retaining uncollected DTO objects. 4. Inspect application source code for static collection maps or unbounded cache registries. Phase 3. Root cause analysis. 1. Evidence collected. Eclipse MAT dominator tree showed 78% of total heap retained by a single concurrent hash map instance inside order event cache. 2. Primary root cause. A static concurrent hash map used to cache order event payloads was initialized without eviction policies or TTL expiration, causing millions of DTO objects to remain permanently rooted in the old generation. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. If sufficient healthy replicas exist, first capture a heap dump from an affected pod if possible, and then perform a rolling pod restart using kubectl rollout restart to flush accumulated heap memory and restore immediate customer transaction processing. 2. Permanent resolution. Replace the raw concurrent hash map cache with a caffeine-bounded cache configured with explicit maximum size of 10,000 and expire after write with 30, time unit. Minutes. 3. Validation. Redeploy to staging and prod, run synthetic load tests, and confirm Grafana heap baselines stabilize after GC cycles. Phase 5. Recurrence prevention. 1. Enforce mandatory -xx : plus heap dump on out-of-memory error, and -xx : heap dump path equals /temp/heap. Hprof JVM flags across all base Docker images. 2. Configure Prometheus or Grafana memory slope alerts to trigger if post-full GC heap usage exceeds 85% for 3 consecutive cycles. 3. Enforce static code analysis rules SonarQuebec flagging static non-final collection maps lacking explicit eviction bounds. Pro tip interview insight. A true memory leak appears on APM charts as a stair-step pattern where post-GC heap baselines steadily rise over time. Always configure -XX: plus heap dump on out-of-memory error in production container arguments, so the JVM automatically writes a diagnostic.hprof file when an occurs.
Follow up when expected. A logical continuation of the incident. How do you analyze a Java heap dump using Eclipse MAT to locate leak suspects and trace GC routes?
Answer: in Eclipse MAT, open the leak suspects report to view high-level memory accumulators. Next, inspect the dominator tree sorted by retained heap size to pinpoint which object tree holds the memory. Finally, right-click the suspect object and select Path to GC routes to exclude weak or soft references to reveal the exact hard reference chain holding the object in heap.
Follow up 2 deeper. Experienced tester. What is the difference between a memory leak and memory bloat in Java applications?
Answer: a memory leak occurs when objects that are no longer needed by business logic remain permanently referenced by GC routes like static maps, preventing GC reclamation and eventually causing Memory bloat occurs when an application creates excessively large, short-lived objects, like reading a 500 megabytes payload entirely into heap, causing temporary memory spikes and GC pauses without leaking memory long-term.
Follow up 3 curveball. What if a container is configured with -XX: plus heap dump on out of memory error, but the pod is killed by the OS kernel exit code 137 before the JVM can write the heap dump file to disk?
Answer: this happens when total container process memory exceeds the Kubernetes cgroup limit, causing the Linux kernel killer to send sigkill exit code 137. Because sigkill immediately terminates the process, the JVM cannot execute shutdown hooks or write heap dumps. To diagnose, raise container limits or take manual heap dumps JCMD 1gc.heap_dump when heap usage reaches 80% prior to kernel termination.
Production Incident 20. A high-throughput REST API microservice experiences severe latency degradation, where HTTP P99 response times jump from 50 milliseconds to over 8 seconds. APM dashboards reveal the JVM spending 40% of its runtime executing full garbage collection cycles. As the on-call Java application support engineer, how do you resolve this GC thrashing outage?
Answer: when an application experiences severe latency spikes due to continuous full GC pauses, my priority is to analyze unified GC logs, tune generation heap ratios, and eliminate premature object promotion using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Grafana APM charts for GC pause frequency, GC time percentage, and AP IP99 or P999 latency spikes. 2. Verify whether latency degradation impacts all microservice replicas or only specific high-throughput pods. 3. Check thread dumps using kubectl exec to verify if worker threads are blocked during stop the world GC pauses. Phase 2. Investigation and evidence gathering. 1. Enable unified JVM GC logging via -xlog::gc star, GC plus phases equals debug: file equals /temp/gc.log::time, uptime, PID: file count equals 5, file size equals 50 megabytes. 2. Analyze gc.log files using GC Easy or jstat-gc util 1000 to monitor Eden, Survivor, and old gen occupancy rates. 3. Check object promotion rates from young gen to old gen to identify premature promotion patterns. 4. Run allocation profiling using async profiler as prof-e alloc-d30-f/temp/alloc.html1 to identify heavy object allocation methods. Phase 3. Root cause analysis. 1. Evidence collected. Unified GC logs showed young gen filling up every 200 milliseconds, with survivor space occupancy at 100% and constant old gen expansion, triggering full GCs every 5 seconds. 2. Primary root cause. Premature object promotion. Application allocation rates exceeded available young generation capacity, causing excessive promotion into old generation. Heap sizing and allocation behavior together triggered continuous full GC cycles. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Increase container memory limits and tune JVM young gen heap ratios -XX: new ratio equals 2 and -XX: max tenuring threshold equals 15. Then perform a rolling pod restart to stop old gen spillage. 2. Permanent resolution. Refactor high allocation. Request loops to reuse object buffers and optimize survivor space sizing so short-lived objects die in young gen. 3. Validation. Confirm GC CPU time drops below 3%, full GC frequency drops to 0, and AP/IP99 latencies return to 50 milliseconds. Phase 5. Recurrence prevention. 1. Configure continuous unified GC logging -xlog::GC star across all base container Docker images. 2. Set Prometheus or Grafana alerts for JVM GC CPU time exceeding 5% for more than 2 minutes. 3. Integrate mandatory memory allocation profiling into pre-release performance benchmark pipelines. Pro tip: interview insight. Frequent full GC pauses are often caused by premature promotion, where short-lived objects spill into old generation before dying. Always check survivor space sizing -XX: survivor ratio and tenuring thresholds -XX: max tenuring threshold to ensure short-lived objects are collected during minor GCs in young gen.
Follow-up when expected. A logical continuation of the incident. How do you interpret a JVM unified GC log-xlog::GC star to determine whether a pause was caused by young GC, mixed GC, or full GC?
Answer. In unified GC logs, garbage collection allocation failure indicates a young GC clearing Eden. Garbage collection G1 evacuation pause mixed indicates a mixed GC collecting young gen plus selected old gen regions. Garbage collection system .gc or full GC indicates a STW full GC scanning the entire heap. Examining pause duration and post-GC heap metrics confirms which phase occurred.
Follow-up 2 deeper. Experienced tester. What is the stop the world STW phase during garbage collection, and how does it affect active thread execution and network timeouts?
Answer. The stop the world phase pauses all application worker threads at JVM safe points, while GC threads manage object references. During a STW pause, the application stops responding to network sockets, causing incoming TCP packets to queue up and triggering connection or read timeouts in upstream API gateways and microservice callers.
Follow-up 3 curveball. What if GC logs show 0 full GCs, but application thread dumps show worker threads blocked on JVM SafePoints? SafePoint synchronize: begin for several seconds.
Answer. This indicates a SafePoint pause delay. The JVM requested a SafePoint, for example, for a minor GC or biased locking revoke, but worker threads executing uncounted loops like long-counted loop constructs without SafePoint polls took seconds to reach a SafePoint. The fix is enabling -XX: plus use counted loop SafePoints or upgrading JVM versions.
Production Incident 21. A Spring Boot microservice utilizing G1GC experiences sporadic 3 to 5 second latency spikes during peak traffic hours. GC logs show frequent to space exhaustion events and full GC fallbacks, violating the target pause time of 200 milliseconds. As the on-call Java application support engineer, how do you resolve these G1GC latency spikes?
Answer. When G1GC experiences to space exhaustion and falls back to full GC pauses, my priority is to analyze G1 region sizing, eliminate humongous allocations, and adjust evacuation thresholds using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM latency distribution charts to correlate 5-second response spikes with G1GC pause timestamps. 2. Check pod status using kubectl get pods to verify if latency spikes trigger Kubernetes liveness probe timeouts. 3. Confirm whether response latency spikes occur during specific high payload business transactions. Phase 2. Investigation and evidence gathering. 1. Review unified GC logs -x log :GC star for entries containing to space exhausted, evacuation failure, or G1 humongous allocation. 2. Analyze G1 heap region sizes and object allocation patterns using a sync profiler allocation mode / as prof-e alloc. 3. Check database query payloads and JSON serialization buffers to identify objects exceeding 50% of a single G1 region size. 4. Review G1 GC tuning parameters including -xx: G1 heap region size, -xx: max GC pause millis, and -xx: initiating heap occupancy %. Phase 3. Root cause analysis. 1. Evidence collected. GC logs showed G1 humongous allocation for 8 MB byte arrays, immediately followed by the space exhausted, and a 4.2-second full GC. 2. Primary root cause. Large PDF export transactions instantiated 8 MB byte arrays that exceeded 50% of the default 4 MB G1 region size. These humongous objects were allocated directly into old gen, fragmenting G1 regions and causing evacuation failures. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Increase G1 region size explicitly using -xx: G1 heap region size equals 16 MB or 32 MB so 8 MB arrays are no longer classified as humongous, then perform a rolling restart. 2. Permanent resolution. Refactor PDF generation code to stream response bytes in chunks directly to HTTP output streams rather than instantiating entire files in memory. 3. Validation. Confirm to space exhausted log entries disappear. G1 pause times remain under -xx: max GC pause millis equals 200 milliseconds and latencies normalize. Phase 5. Recurrence prevention. 1. Calculate and configure optimal -xx: G1 heap region size parameters based on container heap limits during image creation. 2. Implement streaming response patterns across all file export and large payload microservice endpoints. 3. Set Prometheus alerts for G1 humongous object allocation counts in production monitoring. Pro tip interview insight. In G1 GC, any object exceeding 50% of a G1 region size is treated as a humongous object and allocated directly into old gen, causing G1 region fragmentation and evacuation failures. Always tune -xx: G1 heap region size up to 32 MB if your app processes large payloads.
Follow-up when expected. A logical continuation of the incident. How does G1 GC balance young gen and old gen region cleanups to meet target pause times configured via -xx: max GC pause millis?
Answer: G1 GC divides heap into equal-sized regions. It dynamically adjusts young gen region counts and selects a subset of old gen regions with the highest garbage density garbage first during mixed GC cycles, estimating collection time based on historical analytics to satisfy the configured max GC pause millis target.
Follow-up 2 deeper. Experience tester. What is a G1 GC evacuation failure to space exhaustion, and why does it force G1 GC to fall back to a single-threaded full GC?
Answer: Evacuation failure occurs when G1 GC tries to copy live objects from a region being collected into a free survivor or old region, but no free regions remain in heap. Unable to relocate objects, G1 GC stops concurrent operations and triggers a STW single-threaded full GC to compact the entire heap.
Follow-up 3 curveball. What happens if you set -xx: max GC pause millis to an unrealistically low value like 5 milliseconds on a 16 GB heap?
Answer: Setting an impossibly low pause target causes G1 GC to shrink young gen regions dramatically to meet the pause budget. This causes Eden to fill up in milliseconds, triggering extremely frequent young GCs, premature object promotion to old gen, and eventually to space exhaustion leading to long full GC pauses.
Production Incident 22. A Java service in Kubernetes is repeatedly killed by the OS kernel with exit code 137. APM dashboards show JVM heap usage is stable at only 40% of limits, but total container working set memory continuously climbs until exceeding the 2 GB limit. As the on-call Java application support engineer, how do you resolve this native memory leak?
Answer: when container memory climbs despite stable JVM heap usage causing kernel killed events, my priority is to enable native memory tracking, isolate off-heap allocations, and constrain unmanaged native memory using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Confirm container termination cause using kubectl. Describe pod to verify killed state and exit code 137. 2. Check Grafana container working set memory RSS versus JVM heap memory charts to verify off-heap growth. 3. Confirm whether native memory growth correlates with request volume or background processing tasks. Phase 2. Investigation and evidence gathering. 1. Enable JVM native memory tracking by adding -XX: native memory tracking equals summary to container startup arguments. 2. Execute JCMD1NMT baseline followed by JCMD1NMT detail.diff to compare native allocations across metaspace, thread stacks, and direct byte buffers. 3. Inspect worker node kernel logs using dmessage to confirm Linux cgroup memory limit enforcement. 4. Check off heap allocations in third-party native libraries like Natty, JNI, or Zip Inflator. Phase 3. Root cause analysis. 1. Evidence collected. JCMD NMT detail.diff showed symbol and internal categories stable, but Netty direct byte buffers and native malloc allocations grew by 1.2 GB over 4 hours. 2. Primary root cause. A Netty off-heap buffer leak in a custom gRPC client failed to release byte buff references after network transmission, bypassing Java GC and exhausting native OS container memory. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily increase container memory limits only if operationally necessary to stabilize production, while simultaneously mitigating native memory growth by limiting Natty direct memory usage and preparing a code fix. 2. Permanent resolution. Refactor gRPC client code to invoke reference count util.release with byte buff in finally blocks to guarantee off-heap buffer reclamation. 3. Validation. Confirm container RSS memory stabilizes below 1.8 GB and NMT baseline diffs show 0 off-heap leak. Phase 5. Recurrence prevention. 1. Enforce Netty resource leak detection in staging environments by setting -dio.netty.leak-detection.level equals paranoid. 2. Configure native memory tracking and staging-based container images to catch off heap leaks during load testing. 3. Set Grafana alerts monitoring the gap between container working set RSS memory and JVM heap memory. Pro tip interview insight. Linux killer evaluates total process RSS memory heap plus native off heap, not just Java heap. Always enable native memory tracking -XX: native memory tracking equals summary when diagnosing container kills where JVM heap charts look completely healthy.
Follow-up 1 expected. A logical continuation of the incident. How do you use JCMD NMT detail.diff to compare native memory allocations between 2 operational time windows?
Answer. First, establish an initial baseline by executing JCMD PID NMT baseline shortly after application startup. After running traffic for several hours, execute JCMD PID NMT detail.diff. The output calculates exact byte diffs across thread, symbol, native memory, class, and direct byte buffer categories, pinpointing which off-heap component expanded.
Follow-up 2 deeper. Experience tester. What are the primary JVM components that allocate off-heap native memory outside the Java heap?
Answer. Off-heap native memory includes metaspace class metadata. Thread stacks each thread consumes 1 MB by default via -XSS. Direct byte buffers used by NIO and Natty, JIT code cache compiled machine code. Garbage collection data structures, remembered sets in G1GC, and JNI native C or C++ allocations.
Follow-up 3 curveball. What if NMT output shows all JVM native categories metaspace, threads, GC, code cache are completely stable, but container RSS memory still climbs until killed?
Answer. If NMT shows JVM categories are stable while container RSS grows, the native memory leak is occurring outside JVM tracking, typically inside an unmanaged C or C++ native library loaded via JN, such as Zip Inflator or OpenCV that calls malloc directly. I would use Linux OS tools like Address Sanitizer, ASN, or Valgrind or PPROF with Gemalloc to track glibc allocations.
Production Incident 23. A Spring Boot application running dynamic plugin loading and heavy reflection proxy generation crashes with java.lang. Out of memory error metaspace. Subsequent container restarts fail as pods crash repeatedly during boot. As the on-call Java application support engineer, how do you resolve this metaspace exhaustion outage?
Answer. When an application crashes with metaspace out of memory error, my priority is to analyze class loading metrics, isolate class loader leaks, and enforce metaspace bounds using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup logs using kubectl logs to confirm java.lang. Out of memory error metaspace. 2. Check Grafana metaspace memory charts to determine whether metaspace grew gradually over time or spiked suddenly during startup. 3. Confirm whether metaspace exhaustion impacts all microservice replicas or only specific worker nodes. Phase 2. Investigation and evidence gathering. 1. Check class loading and unloading statistics inside running containers using jcmd1vm.class loaders or jstat-class1. 2. Enable class unloading logging by adding -xlog class plus unload equals info to JVM startup arguments. 3. Take a heap dump using jcmd1gc.heap_dump and inspect Eclipse MAT for duplicate class loader instances holding class metadata. 4. Review recent code commits for dynamic proxy generators CGLIB, Groovy script evaluators, or Jackson reflection utils. Phase 3. Root cause analysis. 1. Evidence collected. JStat-class showed class counts continuously climbing past 150,000 classes, and heap dump MAT analysis revealed thousands of uncollected CGLIB $subclass class loader instances. 2. Primary root cause. A dynamic proxy reflection generator inside a custom request validator created a new CGLIB class loader on every incoming HTTP request without caching, causing metaspace to expand until hitting the cap. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Increase the metaspace cap temporarily only to restore production service while immediately investigating and eliminating the underlying class loader leak. 2. Permanent resolution. Refactor dynamic proxy creation code to cache generated proxy classes and reuse shared class loader instances across requests. 3. Validation. Confirm class counts stabilize under load, metaspace usage remains steady at 120 megabytes, and pod health checks pass. Phase 5. Recurrence prevention. 1. Explicitly cap metaspace using -xx: max metaspace size equals 512 megabytes across all containerized JVM startup scripts. 2. Configure Prometheus or Grafana alerts for metaspace usage exceeding 80% of defined max limits. 3. Implement static analysis rules flagging uncached dynamic proxy generation or Groovy class loader instantiations. Pro tip interview insight. Metaspace stores class metadata. Metaspace memory can only be reclaimed when the class loader that loaded those classes is itself garbage collected. If a custom class loader leaks, every class it loaded remains trapped in metaspace forever, leading to metaspace
Follow-up when expected. A logical continuation of the incident. What is the precise architectural difference between perm-gen in Java 7 and metaspace in Java 8 and newer?
Answer. Perm-gen permanent generation was a fixed-size contiguous memory region located inside the Java heap, governed by GC and controlled via -xx: max perm size. Metaspace replaced perm-gen in Java 8, moving class metadata out of Java Heap into off-heap native OS memory, expanding automatically up to native memory limits unless capped via -XX:\max metaspace size.
Follow up 2 deeper. Experienced tester. Why does a class loader leak prevent its loaded classes from being garbage collected in metaspace?
Answer. Classes in metaspace maintain a strong reference back to their defining class loader instance. A class loader can only be garbage collected when all classes it loaded, and the class loader itself have 0 strong references pointing to them. If a single static variable or thread holds a reference to a class loader, every class loaded by it remains pinned in metaspace.
Follow up 3 curveball. How do you configure -XX: compressed class space size and -XX: max metaspace size to prevent metaspace fragmentation on 64-bit JVMs?
Answer. On 64-bit JVMs with compressed OOPS enabled, class metadata pointers are compressed into compressed class space default 1 GB inside metaspace. Setting -XX: compressed class space size equals 256 megabytes and -XX: max metaspace size equals 512 megabytes caps compressed class pointers and general metaspace allocations separately, preventing metaspace native memory fragmentation.
Production Incident 24. An e-commerce backend service exhibits steady heap memory growth over days of continuous operation. Heap dump analysis reveals 70% of total heap memory is consumed by a single static hash map containing millions of stale order context objects. As the on-call Java application support engineer, how do you resolve this collection-based memory leak?
Answer. When a static collection retains stale business objects causing a memory leak, my priority is to inspect GC root reference paths using Eclipse MAT, replace raw collections with bounded eviction caches, and restore heap health using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM heap charts in Grafana to confirm steady old generation memory growth following full GC cycles. 2. Check container memory utilization using kubectl top pods to identify which specific microservice pod is leaking heap. 3. Determine whether memory growth affects order processing latencies or threatens imminent pod crashes. Phase 2. Investigation and evidence gathering. 1. Generate a production heap dump using kubectl exec with jcmd1gc.heap_dump/temp/heap.hprof. 2. Open the heap dump in Eclipse MAT, run the Dominator tree, and inspect top object accumulators. 3. Trace path to GC roots excluding weak or soft references for the top object to identify the static collection holding incoming references. 4. Review source code for static map or list variables where objects are inserted put but never explicitly removed. Phase 3. Root cause analysis. 1. Evidence collected. Eclipse MAT showed 4.2 gigabytes of heap retained by static map string order context cache and order tracking service. 2. Primary root cause. A static hash map used to cache order tracking details appended order context objects on every customer request without calling remove or configuring TTL eviction, creating an uncollectible GC root reference chain. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to flush accumulated heap memory and restore immediate order processing performance. 2. Permanent resolution. Replace the static hash map with a caffeine-bounded cache configured with maximum size 5000 and expire after access 15-time unit.minutes. 3. Validation. Redeploy, run synthetic order load tests, and confirm heap usage stabilizes with post-GC baselines remaining flat. Phase 5. Recurrence prevention. 1. Integrate static code analysis rules SonarQuebec flagging static non-final collections or maps lacking explicit size bounds. 2. Mandate memory profiling using Eclipse MAT or Visual VM during pre-release load testing and staging. 3. Enforce architectural standards requiring caffeine or Redis abstractions for all application caching needs. Pro tip interview insight. Static collection static map. Static list are GC root objects that are never garbage collected during the lifespan of the JVM. Any object added to a static collection remains pinned in memory forever unless explicitly removed. Always use bounded cache abstractions instead of raw static maps.
Follow-up when expected. A logical continuation of the incident. How do you use the path to GC routes feature in Eclipse MAT to determine why an object cannot be garbage collected?
Answer: in Eclipse MAT, select the leaking object in the Dominator tree, right-click, and select Path to GC routes to exclude weak or soft references. MAT traces the chain of strong references backward through the object graph until it reaches the root GC object, such as a static variable, active thread, or JNI handle holding the object pinned in Heap.
Follow-up 2 deeper. Experienced tester. How do weak hash map and soft reference collections differ from standard Java collections when managing memory under GC pressure?
Answer: standard collections hold strong references that prevent GC reclamation. Weak hash map uses weak references for keys, allowing entries to be garbage collected as soon as key objects lose external strong references. Soft reference collections hold objects softly, allowing GC to reclaim them only when JVM heap memory is under severe pressure prior to throwing an
Follow-up 3 curveball. What happens if a custom key object placed inside a hash map does not properly override equals and hash code methods?
Answer: if key objects lack proper equals and hash code overrides, hash map uses object default identity memory addresses. When identical logical keys are inserted on subsequent requests, hash map treats logically identical keys as different objects because equals and hash code are inconsistent, creating duplicate entries, increasing memory usage, degrading lookup performance, and eventually exhausting the heap. This leads to rapid map memory bloat, degraded O of N lookup performance, and eventual heap boom.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 25. Production pods experience continuous heap pressure and eventual out-of-memory error. An automated heap dump is generated, but engineers filtering by shallow heap size misidentify a small 64-byte root object as benign, missing that it retains 80% of total heap memory. As the on-call Java application support engineer, how do you resolve this retained object memory leak?
Answer: when diagnosing heap dumps, my priority is to calculate retained heap sizes across dominator trees, trace incoming strong references to GC roots, and eliminate object retention chains using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Retrieve the production heap dump file /temp/heap.hprof generated prior to pod termination. 2. Check pod restart counts using kubectl. Get pods to verify if memory exhaustion impacts all application instances. 3. Confirm whether transaction latencies degrade steadily as retained objects accumulate in old generation. Phase 2. Investigation and evidence gathering. 1. Open the heap dump in Eclipse MAT Memory Analyzer tool and generate the dominator tree sorted by retained heap. 2. Differentiate between shallow heap object primitive size and retained heap total memory freed upon GC reclamation. 3. Trace path to GC roots excluding weak or soft references to locate the hard reference chain anchoring the retained objects. 4. Inspect source code around top dominator classes for uninvalidated collections or missing session timeout hooks. Phase 3. Root cause analysis. 1. Evidence collected. Eclipse MAT showed a 64-byte session manager instance holding strong references to a deep tree of user session objects retaining 4.8 gigabytes of heap. 2. Primary root cause. Session manager held active references in an internal map without clearing expired sessions, keeping large user state object trees anchored to a GC root and causing heap boom. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. If sufficient healthy replicas exist, capture the heap dump and preserve it for analysis before performing a rolling restart using kubectl rollout restart to flush accumulated retained heap and restore customer session processing. 2. Permanent resolution. Refactor session manager to release strong references upon session expiration and utilize explicit caffeine cache eviction policies. 3. Validation. Confirm retained heap baseline, stabilize under load, and verify memory reclaimed after GC cycles. Phase 5. Recurrence prevention. 1. Conduct engineering training on MAT dominator tree analysis, emphasizing retained heap over shallow heap metrics. 2. Integrate automated heap dump comparison testing into CI and CD performance benchmark pipelines. 3. Configure APM alerts on long-lived retained object counts in old generation. Pro tip interview insight. Shallow heap is the memory consumed by the object itself. Retained heap is the total memory freed when that object is garbage collected. Always sort dominant or trees in Eclipse MAT by retained heap to locate true memory leak routes.
Follow-up when expected. A logical continuation of the incident. How does the Dominator tree in Eclipse MAT calculate retained heap size across an object graph?
Answer. An object X dominates object Y if every reference path from GC routes to Y must pass through X. The retained heap of X is the sum of shallow sizes of X plus all objects dominated by X. MAT computes this tree to determine the exact amount of memory freed if object X were garbage collected.
Follow-up 2 deeper. Experienced tester. What is the difference between incoming references and outgoing references when inspecting an object in MAT?
Answer. Incoming references show which parent objects hold references to the selected object, helping identify the GC root chain keeping it alive. Outgoing references show which child objects the selected object points to, helping identify what data payload the object is retaining.
Follow-up 3 curveball. What if a heap dump analysis shows that 90% of retained heap consists of primitive byte or char arrays, but MAT shows no clear single dominator class?
Answer. This indicates a distributed memory leak across many small objects, such as thousands of uncached string instances or scattered byte buffers. I would use MAT's group by class or duplicate strings tool to identify which business classes instantiate those arrays and optimize string interning or buffer pooling.
Production Incident 26. A high-throughput Netty Spring Web Flux microservice crashes with java.lang. Out-of-memory error direct buffer memory. APM charts show standard Java heap usage is under 30%, but native container memory continuously grows until Netty fails off heap allocations. As the on-call Java application support engineer, how do you resolve this direct byte buffer exhaustion?
Answer. When an application crashes with direct buffer memory out-of-memory error while Java heap usage remains low, my priority is to analyze off-heap direct memory allocations, inspect Netty reference counts, and enforce direct memory limits using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check application error logs using kubectl logs to confirm java.lang. Out-of-memory error direct buffer memory. 2. Compare Grafana JVM heap usage against container working set memory RSS to verify off-heap direct memory growth. 3. Confirm whether direct memory exhaustion impacts all web flux instances or specific high concurrency pods. Phase 2. Investigation and evidence gathering. 1. Execute JCMD1 NMT detail to inspect other and direct byte buffer native memory categories. 2. Review JVM startup arguments to check if -XX:max direct memory size was configured or left uncapped. 3. Inspect custom web flux filters and Netty pipeline handlers for missing data buffer utils.release or reference count util.release calls. 4. Enable Netty off-heap resource leak detection by setting -dio.netty.leak-detection.level equals paranoid in staging. Phase 3. Root cause analysis. 1. Evidence collected. Netty leak detector logs showed leak. ByteBuff.release was not called before being garbage collected inside custom header filter. 2. Primary root cause. A custom web flux filter read incoming HTTP payload data buffer instances without calling data buffer utils.release, leaking off heap direct byte buffer memory until exhausting -XX:, max direct memory size equals 512 megabytes. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily expand direct memory capacity -XX:, max direct memory size equals 1 GB only to stabilize production, while immediately deploying the fix for the leaked data buffer or byte buff references, and perform a rolling restart using kubectl rollout restart to restore immediate service. 2. Permanent resolution. Add data buffer utils.release with data buffer in finally blocks across all custom web flux filter pipelines to ensure off-heap buffers are released. 3. Validation. Confirm netty leak detection logs remain clean, container RSS memory stabilizes, and direct memory metrics remain flat. Phase 5. Recurrence prevention. 1. Cap direct memory explicitly using -XX:\max direct memory size equals 512 megabytes across all containerized netty microservices. 2. Enforce natty leak detection flags in staging integration test suites. 3. Configure Prometheus alerts monitoring direct memory usage exceeding 80% of defined caps. Pro tip interview insight. Direct byte buffers allocate memory directly from OS native memory to achieve zero copy network I/O in natty and NIO. Always set -XX:\max direct memory size when running in containers to prevent natty from exhausting host container RAM.
Follow-up when expected. A logical continuation of the incident. How does the JVM reclaim direct byte buffer memory, and why does GC trigger when direct memory approaches its cap?
Answer. Direct byte buffers use a Java cleaner object sun.misc.cleaner holding a native memory address. When the Java wrapper object is garbage collected, the cleaner frees the native memory. If direct memory allocation reaches max direct memory size, the JVM explicitly triggers system.gc to force collection of unreferenced wrappers and free off heap memory.
Follow-up 2 deeper. Experienced tester. How does Netty's pooled byte buff allocator differ from unpooled direct byte buffer allocations in high-throughput applications?
Answer. Unpooled allocations call OSM alloc/free for every buffer, causing high allocation overhead and thread contention. Natty's pooled byte buff allocator allocates large native memory arenas and reuses chunked byte buffers across requests, significantly reducing OS native allocation overhead and garbage collection activity.
Follow-up 3 curveball. What if -XX max direct memory size is set to 512 megabytes, but Netty's off-heap memory usage continues growing beyond 2 gigabytes until the OS kernel killed the container?
Answer. First, verify whether the application is using Netty's pooled allocator or another native library. If usage exceeds the configured limit, investigate allocator configuration, JNI or native libraries, and container RSS before concluding the leak source, or when unmanaged JNI native libraries call malloc directly. To restrict natty pooled direct memory, set -dio.netty.max direct memory equals 512 megabytes, in addition to the JVM flag, to prevent natty arenas from exceeding container cgroup limits.
Production Incident 27. After a platform upgrade, engineers applied a collection of legacy JVM flags copied from blogs. As a result, the Spring Boot application experiences 100% CPU throttling, low transaction throughput, and frequent 10-second GC pauses under production load. As the on-call Java application support engineer, how do you resolve this JVM overtuning outage?
Answer. When copy-pasted legacy JVM flags degrade application throughput and trigger GC thrashing, my priority is to strip conflicting flags, restore modern JVM ergonomics, and validate performance using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM charts for API throughput RPS drops, 100% CPU saturation, and 10-second response latency spikes. 2. Check active JVM flags using kubectl with jcmd1vm.flags to inventory command line arguments. 3. Verify whether throughput degradation impacts all application pods or only nodes running custom flags. Phase 2. Investigation and evidence gathering. 1. Analyze active JVM arguments via jcmd1vm.flags to locate conflicting options such as combining -XX:+, use parallel GC with G1GC flags, or setting -XX:"max GC pause millis equals 1 millisecond on a 32 GB heap. 2. Enable unified GC logging -xlog:"GC star to evaluate garbage collection phase durations and thread counts. 3. Check Java-XX:+ print flags final to review effective JVM ergonomic defaults calculated by the runtime. 4. Review Git commit logs to identify who introduced custom flags and verify the benchmark justification. Phase 3. Root cause analysis. 1. Evidence collected. JCMD showed -XX:+. Use conc mark sweep GC combined with -XX: new size equals 100 megabytes configured on a Java 17 runtime running on a 16 GB container. 2. Primary root cause. Legacy CMSGC flags deprecated or removed in modern JDKs introduced obsolete and conflicting GC tuning. On Java 17, CMS flags are ignored or rejected depending on the JVM, while conflicting heap tuning caused poor GC ergonomics, excessive GC overhead, and severe throughput degradation. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Strip away all custom legacy GC flags, relying on modern Java 17 ergonomics-XX plus use G1 GC-XX max RAM percentage equals 75.0 and execute a rolling pod restart. 2. Permanent resolution. Standardize clean base container images across microservices with zero custom GC tuning flags. 3. Validation. Confirm CPU usage drops below 40%, API transaction throughput increases 5 times, and GC pause times stay under 200 milliseconds. Phase 5. Recurrence prevention. 1. Implement automated CI and CD performance benchmark gates to validate any proposed JVM flag modifications. 2. Establish strict architecture governance banning copy-pasted JVM tuning options in container manifests. 3. Conduct regular load testing and staging using default container ergonomics to baseline true capacity. Pro tip interview insight. Modern JVMs Java 17 November 2021 have sophisticated ergonomics that self-tune based on container resources. Over-tuning with legacy, Java 8 flags often degrades performance. Start with zero custom GC flags, except -XX: plus use G1 GC, and -XX: max RAM percentage equals 75.0.
Follow-up when expected. A logical continuation of the incident. What happens when -XMS initial heap and -XMX max heap are set to different values in containerized Kubernetes environments versus setting them equal?
Answer. Setting -XMS equal to -XMX pre allocates total heap during startup, preventing latency spikes caused by dynamic heap expansion during traffic bursts. In Kubernetes containers, pre-allocating heap also ensures the container RSS memory footprint is stable from boot, preventing unexpected cgroup kills later when heap expands.
Follow-up 2 deeper. Experience tester. How do JVM ergonomics automatically calculate thread counts parallel GC threads, conc GC threads based on container CPU limits?
Answer. On container startup, the JVM queries cgroup CPU quotas. If a container has 8 CPU cores allocated, G1 GC ergonomics sets parallel GC threads to 8 and conc GC threads to 25% of parallel threads 2 threads. This prevents thread over-provisioning and CPU context switching overhead.
Follow-up 3 curveball. What if a container has a CPU limit of 0.5 cores 500 millicores, and the JVM calculates worker thread pools, assuming a multi-core system?
Answer. On fractional CPU limits less than 1 core, legacy JVMs miscalculated available processors, creating default thread pools fork join pool, Tomcat workers, GC threads sized for the multi-core host. This leads to severe CPU throttling. Modern JVMs correctly interpret fractional cgroups, but setting explicit thread pool caps prevents context switch saturation.
Production Incident 28. An e-commerce microservice experiences intermittent 5-second API freezes whenever users download invoice reports. APM charts show massive CPU spikes and continuous garbage collection activity. Investigation reveals single HTTP requests instantiating 200 megabytes byte array objects in memory. As the on-call Java application support engineer, how do you resolve these GC storms?
Answer. When large object allocations trigger GC storms and API freezes, my priority is to profile allocation hotspots, eliminate in-memory buffer instantiations, and implement streaming response patterns using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Correlate APM-CPU spikes and 5-second latency freezes with specific report download API endpoints. 2. Check pod status using kubectl. Get pods to verify if allocation spikes trigger readiness probe timeouts. 3. Confirm whether memory allocation storms impact all API operations or are isolated to report downloads. Phase 2. Investigation and evidence gathering. 1. Run memory allocation profiling using a sync profiler as prof-e-alloc-d30-f/temp/alloc.html1 during report downloads. 2. Inspect unified GC logs -xlog:(gc* for G1 humongous allocation or Eden allocation failure entries. 3. Review application source code and report service for bulk database fetches. Find all or byte array output stream buffering. 4. Check Jackson object mapper configuration for in-memory string conversions write value as string. Phase 3. Root cause analysis. 1. Evidence collected. A sync profiler allocation flame graph showed 85% of allocations originating from report service.generate invoice calling repository.findAll. 2. Primary root cause. The report endpoint fetched 500,000 database rows into an in-memory array list and buffered a 200 megabytes JSON string before writing to HTTP output, triggering G1GC humongous allocation storms and STW pauses. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily throttle or rate limit large report downloads if necessary while rolling out the streaming implementation and execute a rolling restart to stabilize pod CPU. 2. Permanent resolution. Refactor report service to stream database rows using Spring data stream of invoice and stream CSV or JSON chunks directly to the HTTP response output stream. 3. Validation. Confirm 200 megabytes allocations disappear from allocation profiles. CPU remains under 20% during downloads, and latencies remain under 100 milliseconds. Phase 5. Recurrence prevention. 1. Mandate chunk transfer encoding for all report, export, and large payload microservice endpoints. 2. Enforce Jackson sequence writer streaming serializers across all file generation services. 3. Integrate automated memory allocation profiling assertions into CI and CD performance benchmark tests. Pro tip interview insight. Allocating large objects greater than 50% of G1 region forces the JVM into frequent GC cycles. Never read entire multi-megabyte datasets into memory lists or string builders. Always stream large datasets from the database directly to the HTTP output stream.
Follow up when expected. A logical continuation of the incident. How does Spring Data JP, a streaming stream of T, differ from returning a list of T when processing large database query result sets?
Answer. Returning list of T fetches all matching database rows at once, instantiating thousands of entity objects in Java Heap simultaneously. Returning stream of T uses a database cursor to fetch and process rows one by one in chunks, keeping JVM heap memory usage constant regardless of whether the table contains 10 rows or 10 million rows.
Follow up 2 deeper. Experience tester. How do Jackson Streaming API's JSON generator allow low-memory JSON serialization compared to object mapper.write value as string?
Answer. Object mapper.write value as string builds the entire serialized JSON string in memory as a single character array before returning. Jackson's JSON generator streams JSON tokens directly to the underlying HTTP response output stream in small byte buffers, preventing large heap memory allocations.
Follow up 3 curveball. What if a service must process a 2 GB XML or CSV file uploaded by a user without running out of heap memory?
Answer. I would use a push-based streaming parser like StackS Streaming API for XML, or a chunked CSV parser like Apache Commons CSV, combined with Spring Web Flux file streaming. This parses and processes file records event by event as bytes arrive over the network, maintaining a tiny 8 kilobytes heap footprint even for multi-gigabyte files.
Production Incident 29. A legacy financial service exhibits gradual performance degradation and high CPU usage in the java.lang.ref.finalizer thread. Heap dumps reveal millions of uncollected objects waiting in the finalizer queue, causing severe GC delays and eventual out-of-memory error. As the on-call Java application support engineer, how do you resolve this finalizer bottleneck?
Answer: when an application experiences severe GC delays due to finalizer queue backup, my priority is to inspect finalizer thread states, replace finalize overrides with auto-closable, and enforce modern resource management using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect thread dumps using JCMD OneThread.print to check the state and queue backlog of the finalizer daemon thread. 2. Check Grafana APM metrics for GC pause duration increases and old generation memory accumulation. 3. Confirm whether finalizer thread queue backup impacts transaction latency across all application pods. Phase 2. Investigation and evidence gathering. 1. Inspect heap dumps in Eclipse MAT to examine java.lang.ref.finalizer objects and reference queues. 2. Trace outgoing references from finalizer queue objects to identify legacy classes overriding the finalize method. 3. Review application source code for legacy native resource wrappers such as native socket or file handles relying on finalize. 4. Verify whether soft reference or phantom reference caches fail to clear under GC pressure. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed thread finalizer in waiting state while processing a 2 million object queue of native socket wrapper. 2. Primary root cause. Legacy classes overridden finalize to clean up native socket handles because objects with finalize methods require processing by a single-threaded JVM finalizer daemon. The queue backed up under high throughput, delaying memory reclamation across 2+ GC cycles. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to flush the backed up finalizer queue and recover processing performance. 2. Permanent resolution. Remove all finalize overrides, replacing them with auto-closable and try with resources blocks for explicit resource cleanup. 3. Validation. Confirm finalizer thread queue remains empty under load, GC pause durations drop 80%, and heap baselines flatten. Phase 5. Recurrence prevention. 1. Enforce static code analysis rules SonarQuebec prohibiting finalize method overrides across all repositories. 2. Replace soft reference memory caches with caffeine explicit TTL caches. 3. Standardize Java 9 plus Cleaner API for any mandatory native resource cleanup abstractions. Pro tip interview insight. Never override finalize. Objects with finalizers typically require at least 2 garbage collection cycles before reclamation, introducing unpredictable latency, because the JVM must enqueue them into a single-threaded finalizer queue first. Use try with resources or Java 9 Cleaner API for safe, instant resource cleanup.
Follow-up 1 expected. A logical continuation of the incident. Why are finalize methods deprecated in Java 9 and marked for removal in newer JDK versions?
Answer: finalizers introduce severe performance overhead, unpredictable execution timing, thread deadlocks, and memory leaks. The single-threaded finalizer daemon thread cannot keep up with high object allocation rates, delaying GC reclamation across multiple cycles and exposing applications to security resurrection vulnerabilities.
Follow-up 2 deeper. Experienced tester. How do soft reference and phantom reference differ in reclamation behavior under JVM memory pressure?
Answer: soft reference objects are cleared at the discretion of the garbage collector only when heap memory is under severe pressure prior to throwing an making them useful for memory-sensitive caches. Phantom reference objects are never automatically cleared by GC. They are enqueued into a reference queue after the object is finalized, allowing explicit post-mortem cleanup.
Follow-up 3 curveball. How does Java 9 java.lang.ref.cleaner AP, I overcome the single-threaded bottleneck of legacy finalizers.
Answer: the Cleaner API uses phantom references managed by dedicated, configurable thread pools rather than a single global finalizer thread. Cleaning actions are registered as lightweight runnable tasks that execute asynchronously when an object becomes phantom reachable, without delaying standard garbage collection cycles.
Production Incident 30. Following a production release and JDK upgrade to Java 17, a payment microservice boots successfully, but when a payment gateway API is invoked, transactions fail with java.lang.no class def found error. Java x/xml/bind/JAXB exception. As the on-call Java application support engineer, how do you resolve this runtime class resolution outage?
Answer: when an application boots cleanly but throws no class def found error at runtime, my priority is to isolate JDK module removals, inspect compiled fat jar class paths, and add explicit dependency bindings using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check application error logs using kubectl logs to capture the exact stack trace and missing class path. 2. Confirm whether the runtime class failure impacts 100% of payment transactions or only specific JAXB serialization paths. 3. Verify recent build commit logs to check if Java version upgrades such as Java 8 to Java 17 were executed. Phase 2. Investigation and evidence gathering. 1. Inspect full stack trace for java.lang.no class def found error java x/xml/bind/JAXB exception. 2. Inspect the compiled fat jar class path using jar-tf to verify if JAXB API classes are packaged inside the artifact. 3. Check project build files pom.xml to verify if JAXB dependencies were assumed to be provided by the JDK core. 4. Review static initializer blocks in calling classes to check if an unhandled exception in initializer error occurred previously. Phase 3. Root cause analysis. 1. Evidence collected. Runtime logs showed no class def found error. Java x/xml/bind/JAXB exception when executing XML payment response marshalling. 2. Primary root cause. JDK 11 plus module system migration. The application relied on Java 8 bundled JAXB modules, which were permanently removed from JDK core in Java 11 plus, causing runtime class lookup failures when payment code executed. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Add explicit Jakarta XML binding dependencies jakarta.xml.bind API and JAXB runtime to pom.xml, rebuild artifact and perform an emergency rolling deployment. 2. Permanent resolution. Audit all microservice repositories for deprecated JDK core dependencies and enforce explicit Jakarta EE dependencies across all build files. 3. Validation. Confirm payment API workflows execute cleanly, verify XML marshalling succeeds, and monitor error rates. Phase 5. Recurrence prevention. 1. Integrate JDK migration compatibility, plugins such as Open Rewrite or JDEPs into CI and CD pipelines to catch removed JDK modules pre-build. 2. Mandate explicit dependency declaration in pom.xml rather than relying on JDK implicit classpath modules. 3. Execute full integration regression test suites in staging prior to production JDK version upgrades. Pro tip interview insight. Class not found exception occurs when Java dynamically loads a class via reflection class dot for name, and the file is missing. No class def found error occurs when a class was available during compilation, but its definition cannot be loaded at runtime, often due to static initializer failures or removed JDK modules.
Follow up when expected. A logical continuation of the incident. How do you diagnose a no class def found error caused by a failed exception in initializer error in a static block?
Answer. Inspect application startup logs for an earlier exception in initializer error or class not found exception thrown inside a static block or static field assignment. When a static initializer fails once, the The JVM marks that class as uninitializable. Subsequent attempts to reference that class throw no class def found error rather than repeating the original exception.
Follow up 2 deeper. Experience tester. What tool JDEPs can you run during CI and CD builds to analyze dependencies and identify removed JDK modules before upgrading Java versions?
Answer: JDEPs is the Java dependency analysis tool built into the JDK. Executing JDEPs-JDK internals artifact.jar scans compiled class files for dependencies on internal or removed JDK APIs like sun.misc.base64 encoder or javax.xml.bind, allowing developers to replace deprecated modules before deploying JDK upgrades.
Follow up 3 curveball. What if a no-class def found error occurs in a multi-class loader environment like OSGI or Tomcat, where the class file exists in a sibling class loader, but is hidden from the current thread context class loader?
Answer: this is a class loader isolation visibility error. In hierarchical or modular class loader systems, parent class loaders cannot see classes loaded by child or sibling class loaders. To resolve, explicitly set the thread context class loader thread.currentThread.setContext class loader, or configure the appropriate module export or import rules, or adjust the thread context class loader so the target class loader can resolve the class.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 31. A Spring Boot microservice upgraded to Java 17 boots, but fails at runtime when reflection is invoked on internal JDK classes, throwing inaccessible object exception. Unable to make protected final java.lang class accessible. Module java.base does not opens java.lang to unnamed module. As the on-call Java application support engineer, how do you resolve this jigsaw reflection outage?
Answer: when a Java 17 platform upgrade triggers reflection access exceptions due to strong module encapsulation, my priority is to configure command line module export flags, upgrade incompatible libraries, and restore runtime access using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup and runtime logs using kubectl logs to capture the exact java.lang. Reflect .inaccessible object exception. 2. Identify the specific internal JDK package such as java.lang or java.util being accessed illegally via reflection. 3. Confirm whether reflection failures impact all microservice workflows or only specific serialization paths. Phase 2. Investigation and evidence gathering. 1. Inspect stack traces to identify the calling third-party library such as older versions of Jackson, CGLIB, or Lombok. 2. Review JVM startup arguments in Kubernetes deployment manifests for missing Java module system jigsaw export flags. 3. Test command line module opening options --add opens equals java.base/java.lang equals all unnamed in staging. 4. Check build files pom.xml for outdated third-party library versions lacking Java 17 module compatibility. Phase 3. Root cause analysis. 1. Evidence collected. Runtime logs showed inaccessible object exception when Jackson tried to reflectively access java.lang class fields. 2. Primary root cause. Java 17 strongly encapsulates JDK internal packages by default project jigsaw. An outdated Jackson library attempted deep reflection on java.lang without explicit --add opens JVM flags or updated Java 17 library modules. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily add the required JVM startup argument --add opens equals java.base/java.lang equals all unnamed to deployment manifests only to restore production service, while simultaneously preparing an upgrade of the incompatible library so the workaround can be removed and perform a rolling restart to immediately bypass encapsulation. 2. Permanent resolution. Upgrade third-party dependencies Jackson Spring, CGLIB to Java 17 plus compliant versions and remove temporary --add opens flags. 3. Validation. Confirm reflection exceptions disappear, synthetic workflows pass, and pod health checks show 1 out of 1 ready. Phase 5. Recurrence prevention. 1. Run open rewrite or JDEPS migration analysis plugins in CI and CD pipelines to detect illegal reflective access pre-build. 2. Mandate third-party library version compatibility audits prior to major JDK upgrades. 3. Enforce architecture guardrails, eliminating custom deep reflection on JDK internal packages. Pro tip interview insight. Java 17 Plus strongly encapsulates JDK internals by default, while --add opens provides an immediate production workaround for inaccessible object exception. The long-term solution is upgrading third-party libraries like Jackson and CGLIB to versions compatible with Java 17 module encapsulation.
Follow up when expected. A logical continuation of the incident. What is the precise architectural difference between --add opens and --add exports in the Java module system?
Answer: --add exports public types of a module package to other modules at compile time and runtime, permitting standard public API access. --add opens a package for deep reflective access at runtime, allowing set accessible with true calls on private and protected members of that package.
Follow up 2 deeper. Experience tester. How did JVM behavior regarding illegal reflective access change between Java 11-illegal access equals permit and Java 17-illegal access equals deny?
Answer: in Java 11, --illegal access equals permit was the default, issuing a single console warning on deep reflection while permitting access. In Java 17, --illegal access equals deny became mandatory, completely blocking illegal reflective access to JDK internal packages and throwing inaccessible object exception, unless explicitly opened via --add opens.
Follow up 3 curveball. What if adding --add opens resolves reflection errors for java.lang, but third-party serialization code fails attempting reflection on java.util.collections $unmodifiable collection?
Answer: this requires opening the java.util package as well. I would append --add opens equals java.base/java.util equals all unnamed to the JVM startup options. The long-term fix remains upgrading the serialization framework such as Cryo or Jackson to a version that uses official public APIs or dedicated Java 17 custom serializers.
Production Incident 32. A legacy Spring microservice upgraded from Java 8 to Java 17 crashes during XML payload processing with class not found exception. javax.xml.bind.jaxb context. As the on-call Java application support engineer, how do you resolve this missing JAXB module outage?
Answer: when a Java platform upgrade breaks XML payload processing due to JEE module removal, my priority is to inspect class path dependencies, add explicit Jakarta XML binding libraries, and migrate package references using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup logs using kubectl logs to confirm java.lang.class not found exception. javax.xml.bind.jaxb context. 2. Determine whether XML processing failures impact 100% of payment or SOAP transactions or specific endpoints. 3. Verify build commit logs to confirm recent Java version upgrades from Java 8 to Java 17. Phase 2. Investigation and evidence gathering. 1. Review project pom.xml or build.gradle for missing explicit JAXB API and runtime implementation dependencies. 2. Inspect compiled fat jar contents using jar-tf to confirm if javax.xml.bind classes are absent from the artifact. 3. Check whether application code imports legacy javax.xml.bind or modern jakarta.xml.bind package namespaces. 4. Verify whether underlying SOAP web service client stubs require Jakarta XML binding migration. Phase 3. Root cause analysis. 1. Evidence collected. Runtime logs showed class not found exception javax.xml.bind.jaxb context during XML unmarshalling. 2. Primary root cause. Java 11 permanently removed JEE modules including JAXB from the core JDK distribution. The microservice relied on Java 8 bundled JAXB APIs without declaring explicit external Maven dependencies. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Add explicit Jakarta XML binding dependencies jakarta.xml.bind API and JAXB runtime to pom.xml. Rebuild artifact and perform a rolling deployment. 2. Permanent resolution. If migrating to Jakarta EE9+, update application source code and SOAP stubs to jakarta.xml.bind. Otherwise, applications remaining on the Java EE ecosystem may continue using javax.xml.bind with explicit JAXB dependencies. 3. Validation. Confirm XML unmarshalling executes cleanly, payment endpoints return 200 OK, and synthetic tests pass. Phase 5. Recurrence prevention. 1. Audit all microservice repositories for deprecated Java EE core dependencies before executing JDK upgrades. 2. Integrate rewrite automated migration recipes into CI and CD pipelines to upgrade JavaX packages to Jakarta. 3. Enforce explicit dependency declarations in pom.xml rather than relying on implicit JDK core modules. Pro tip interview insight. Java 11 removed JEE modules JAXB, JTA, WS from the core JDK. When upgrading from Java 8, never assume XML or SOAP APIs are bundled in the JDK. Always explicitly add jakarta.xml.bind API and JAXB runtime dependencies to pom.xml.
Follow up when expected. A logical continuation of the incident. What is the namespace migration difference between legacy javax.xml.bind and modern jakarta.xml.bind?
Answer. Oracle transferred Java EE technologies to the Eclipse Foundation under Jakarta EE. Due to trademark restrictions, package namespaces changed from javax.star to jakarta.star. Migration requires replacing javax.xml.bind.star, imports with jakarta.xml.bind.star, and upgrading build dependencies to Jakarta EE9+ standards.
Follow up 2 deeper. Experienced tester. How do you configure Maven dependency : analyze in CI and CD pipelines to flag implicit JDK dependencies before upgrading Java versions?
Answer. Running MVN dependency : analyze scans project bytecode and compares used dependencies against declared dependencies in pom.xml. It flags used undeclared dependencies, classes referenced in code that are missing explicit pom.xml declarations, allowing engineers to fix missing dependencies prior to JDK upgrades.
Follow up 3 curveball. What if adding jakarta.xml.bind API resolves class loading, but XML marshalling fails at runtime with JAXB exception implementation of JAXB context could not be found?
Answer. This happens when the JAXB API specification dependency is present on the class path, but the underlying implementation runtime is missing. JAXB uses service loader to locate an implementation. To fix, add the glassfish JAXB runtime or org.glassfish.jaxb::JAXB runtime dependency to pom.xml.
Production incident 33. After expanding a high-memory microservice container heap from 30 GB to 34 GB, total memory footprint jumps dramatically by 40%, GC pause times increase, and containers suffer sudden killed events. As the on-call Java application support engineer, how do you resolve this compressed oops threshold breach?
Answer. When expanding Java Heap beyond 32 GB triggers unexpected memory bloat due to disabled compressed oops, my priority is to analyze object pointer compression thresholds, right-size heap bounds below 31 GB, and restore 32-bit pointer efficiency using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect container working set memory RSS in Grafana to confirm a 40% memory footprint jump after increasing heap to 34 GB. 2. Check pod termination status. Using kubectl, get pods to verify if containers are suffering kernel killed events. 3. Confirm whether GC pause durations increased significantly following the Heap expansion release. Phase 2. Investigation and evidence gathering. 1. Check active compressed OOPS status inside running containers using JCMD1VM.flags or Java-XX : plus print flags final-version pipe grep use compressed OOPS. 2. Verify whether JVM flag-XX : plus use compressed OOPS was automatically disabled when Heap crossed the 32 GB threshold. 3. Compare object header sizes and reference pointer sizes 4 bytes versus 8 bytes between 30 GB and 34 GB heaps. 4. Inspect GC logs-xlog::GC* to evaluate garbage collection object scanning overhead with 64-bit uncompressed pointers. Phase 3. Root cause analysis. 1. Evidence collected. JCMD showed use compressed OOPS equals false when Heap was configured to -XM-X34G. 2. Primary root cause. Setting Heap to 34 GB crossed the practical compressed OOPS threshold for this JVM configuration. The JVM disabled 32-bit object pointer compression, increasing object pointer size and overall object memory footprint significantly, depending on the application's object layout and allocation profile. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Reduce JVM heap size back down to 31 GB XM-X31G to re-enable compressed OOPS and perform a rolling pod restart to restore memory efficiency immediately. 2. Permanent resolution. Scale application capacity horizontally by adding more 16 GB or 31 GB pod replicas rather than expanding single pod heaps beyond 32 GB. 3. Validation. Confirm JCMD1VM.flag shows use compressed OOPS equals true, container RSS drops 40% and GC pauses normalize. Phase 5. Recurrence prevention. 1. Establish architecture guardrails capping individual container heaps at 31 GB XM-X31G across all microservices. 2. Configure CI and CD deployment linter rules blocking -XMX configurations between 32 GB and 48 GB. 3. Mandate horizontal auto-scaling HPA policies for capacity scaling instead of single pod vertical heap bloating. Pro tip interview insight. Heap sizes slightly above the compressed OOPS threshold should be benchmarked carefully. In many workloads, a heap around 30 to 31 GB with compressed OOPS enabled provides better memory efficiency than a slightly larger heap without it.
Follow-up 1 expected. A logical continuation of the incident. How does compressed OOPS encode 64-bit object memory addresses into 32-bit pointers using 8-byte object alignment?
Answer. Since JVM objects are aligned on 8-byte boundaries, the lowest 3 bits of every object address are always 0. Compressed OOPS drops these 3 0 bits when storing pointers, effectively bit-shifting 32-bit addresses left by 3 bits upon decoding. This allows 32-bit pointers to address up to 32 GB 2 to the power of 35 bytes of heap memory.
Follow-up 2 deeper. Experience tester. How does -XX object alignment in bytes allow compressed OOPS to support heaps up to 64 GB, and what are the memory overhead trade-offs?
Answer. Setting -XX: object alignment in bytes equals 16 aligns objects on 16-byte boundaries, allowing 32-bit pointers to shift by 4 bits and address up to 64 GB heap. However, the trade-off is object padding bloat. Small objects require extra padding bytes to reach 16-byte alignment, which can offset pointer compression savings.
Follow-up 3 curveball. What if a service strictly requires a 64 GB heap for massive in-memory caching, and compressed OOPS is disabled? How do you optimize object layout to reduce 64-bit pointer bloat?
Answer. To minimize 64-bit pointer overhead on large heaps, offload large byte arrays and cache objects off heap using direct byte buffers or off-heap caches like Chronicle Map. Use primitive collections like Fastutil or Eclipse collections to avoid object wrapper overhead, and tune G1 region size to 32 MB.
Production incident 34. A high-throughput Java service runs normally for 3 days, but then experiences a permanent 10 times drop in transaction throughput and 100% CPU utilization. Application logs show code cache is full. Compiler has been disabled. As the on-call Java application support engineer, how do you resolve this JIT compiler degradation?
Answer: when code cache exhaustion permanently disables JIT compilation, causing catastrophic throughput degradation, my priority is to analyze code cache utilization, expand reserved code cache size, and enable code cache flushing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics for sudden, permanent transaction throughput drops 10 times RPS drop, accompanied by 100% CPU utilization. 2. Check application standard out and standard error logs for Java hotspot with TM64-bit server VM warning. Code cache is full. Compiler has been disabled. 3. Confirm whether JIT compiler shutdown impacts all service replicas or only long-running worker pods. Phase 2. Investigation and evidence gathering. 1. Inspect code cache utilization using JCMD1 compiler.code cache or JStat-compiler1. 2. Check active JVM arguments to verify the value configured for -XX reserved code cache size. 3. Verify whether C2 JIT compilation tier was disabled and confirm if threads are executing exclusively in slow interpreted mode. 4. Inspect application code for heavy dynamic class generation CGLIB proxies, reflection wrappers, or groovy scripts filling code cache. Phase 3. Root cause analysis. 1. Evidence collected. JCMD compiler.code cache showed 240 megabytes reserved code cache 100% utilized, with compilation equals disabled. 2. Primary root cause. Continuous dynamic class generation filled the default 240 megabytes code cache -XX : reserved code cache size equals 240 megabytes. Lacking -XX : plus use code cache flushing. The JVM disabled the JIT C2 compiler permanently, forcing the app into interpreted mode. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Expand code cache size -XX : reserved code cache size equals 512 megabytes and enable flushing -XX : plus use code cache flushing, then perform a rolling restart to restore JIT compilation. 2. Permanent resolution. Refactor dynamic proxy creation to reuse compiled classes and standardize code cache sizing in base JVM container templates. 3. Validation. Confirm JCMD compiler.code cache shows active compilation status, CPU utilization drops, and RPS throughput recovers. Phase 5. Recurrence prevention. 1. Configure explicit code cache sizing -XX : reserved code cache size equals 512 megabytes and flushing flags across all base Docker images. 2. Set Prometheus or Grafana alerts monitoring code cache memory usage exceeding 80% of reserved capacity. 3. Profile JIT compilation activity and code cache growth using Java Flight Recorder JFR during load testing. Pro tip interview insight. The JVM code cache stores native machine code generated by the JIT compiler. Tune reserved code cache size according to workload characteristics and monitor utilization. Many high-throughput services benefit from larger code caches, but there is no universally correct value.
Follow-up 1 expected. A logical continuation of the incident. What is the difference between C1 and C2 JIT compilation tiers in Java, and how are they stored in segmented code cache?
Answer: C1 client compiler compiles code quickly with basic optimizations for fast startup. C2 server compiler performs aggressive, heavily optimized native compilation for hot execution paths. In segmented code cache Java 9+, native code is split into non-end methods JVM internal, profiled end methods C1 compiled, and non-profiled end methods C2 compiled.
Follow-up 2 deeper. Experience tester. How does -XX+ use code cache flushing prevent JIT compilation shutdown when code cache approaches capacity?
Answer: when enabled, -XX : use code cache flushing instructs the JVM to sweep the code cache when it reaches capacity. It discards cold, infrequently executed C2 compiled methods, and revoke stale speculative optimizations, freeing native space so hot methods can continue being compiled by JIT.
Follow-up 3 curveball. What if code cache is sized to 512 megabytes, but JIT compilation CPU usage remains at 100% due to continuous JIT optimization's uncommon traps?
Answer: this indicates JIT optimization thrashing uncommon trap loops. It occurs when polymorphic code, or changing runtime types, invalidates C2 optimistic assumptions, forcing C2 to optimize to C1 or interpreted mode, only to recompile and to optimize repeatedly. I would analyze JFR compiler invalidation events to refactor polymorphic interface calls.
Production Incident 35. A Java microservice abruptly terminates without throwing any Java exception or executing JVM shutdown hooks. Kubernetes reports pod termination with exit code 139 sigsegv, and a fatal crash file named hs_error_PID1.log is generated. As the on-call Java application support engineer, how do you resolve this fatal JVM crash?
Answer: when a fatal native crash generates an hs_error_PID log file and terminates the JVM, my priority is to analyze the problematic native frame, isolate JNI or C2 compiler defects, and apply native stability patches using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Confirm container exit reason using kubectl describe pod to verify exit code 139 sigsegv native segmentation fault. 2. Retrieve the fatal crash log file hs_error_PID1.log from the container working directory or persistent mount. 3. Determine whether fatal native crashes occur randomly across the pod fleet or correlate with specific native library calls. Phase 2. Investigation and evidence gathering. 1. Open hs_error_PID1.log and inspect the problematic frameline in the log header to identify the native library, for example .so or .dll. 2. Examine the thread section to analyze the Java and native C or C++ stack trace of the crashing thread. 3. Review VM state and register state in the crash log to verify if the crash occurred during GC, JIT compilation, or native execution. 4. Check worker node kernel logs dmessage or journal CTL-K to determine whether the crash was accompanied by hardware memory errors, kernel faults, or events. Phase 3. Root cause analysis. 1. Evidence collected. hs_error_PID1.log showed problematic frame C libimage processor .so plus 0x12A40 with sigseg v0x8 zeros. 2. Primary root cause. A C or C++ third-party image processing JNI native library attempted an illegal memory read at a null pointer address inside native code, triggering a sigseg v segmentation fault that crashed the entire JVM process. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Disable the image processing feature flag or roll back to an earlier native library build, then perform a rolling pod restart to restore service. 2. Permanent resolution. Upgrade the third-party JNI library to a patched memory-safe version, or isolate native library invocation into a sidecar worker process. 3. Validation. Confirm 0% native crashes, verify image processing transactions complete, and monitor pod uptime. Phase 5. Recurrence prevention. 1. Configure -xx:"error file equals /temp/hs_error_pid%p.log in base Docker images to route crash logs to persistent volume mounts. 2. Mandate static C or C++ memory safety audits and Valgrind profiling on all custom JNI native libraries. 3. Implement out-of-process isolation for third-party C or C++ native dependencies to protect the main JVM process. Pro tip interview insight. An hs_error_PID.log file is generated when the JVM suffers a fatal native crash sigseg v or exit code 139. Always inspect the problematic frameline first. If it points to a .so or .dll library, the crash is in a JNI native library. If it points to libjvm.so, it may be a JIT compiler or JVM bug.
Follow-up 1 expected. A logical continuation of the incident. How do you interpret the problematic frame and VM state sections in an hs_error_pid.log file to isolate JNI native crashes from JIT C2 compiler crashes?
Answer: in hs_error_pid.log, the problematic frame specifies the exact library executing when the crash occurred. A frame starting with clibxyz.so indicates an unmanaged JNIC or C++ code crash. A frame starting with J or V inside libjvm.so during VM state. Compiling indicates a JIT C2 compiler bug during bytecode optimization.
Follow-up 2 deeper. Experienced tester. What JVM flags -xx:(error or -xx:(error file can you configure to automatically execute diagnostic scripts or capture core dumps when a fatal JVM crash occurs?
Answer: -xx:(error file equals /var/log/jvm/hs_error_%p.log specifies the crash log output path. -xx:(error equals gcore%p or -xx:(error equals /script/notify_sre.sh%p executes custom shell scripts upon crash, allowing SREs to automatically generate a Linux core dump or trigger P1, alerting when a native crash occurs.
Follow-up 3 curveball. What if an hs_error_pid log shows the crash occurred inside libjvm.so during C2 JIT compilation compile broker? How do you disable JIT compilation for that specific problematic method using -xx:(compile command?
Answer: if a JIT compiler bug triggers a fatal JVM crash on a specific method, I configure -xx:(compile command equals exclude /example/payment service.process_transaction in the JVM startup flags. This instructs the C2 compiler to skip JIT compilation for that single method and execute it in interpreted mode, preventing the crash until a JDK patch is applied.
Production Incident 36. A mission-critical trading service experiences unpredictable 2-second transaction latency spikes in production. Standard logging and APM metrics show normal CPU and heap usage, but cannot isolate the root cause. As the on-call Java application support engineer, how do you use Java Flight Recorder, JFR, to investigate this low-overhead production latency?
Answer: when standard APM metrics fail to explain transient latency spikes, my priority is to capture a low-overhead JFR recording in production, analyze thread lock contention and I/O events in JDK mission control, and apply fixes using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Confirm that APM metrics show normal overall CPU and heap levels despite intermittent 2-second transaction latency spikes. 2. Verify that thread dumps taken during spikes show threads in blocked or timed_waiting states on I/O streams. 3. Prepare to initiate a low-overhead Java Flight Recorder JFR profiling session on live production pods. Phase 2. Investigation and evidence gathering. 1. Trigger a 2-minute JFR recording on the live pod using jcmd1jfr.startName equals prod profile settings equals profile duration equals 120 seconds file name equals /temp/profile.jfr. 2. Download /temp/profile.jfr and open it in JDK Mission Control JMC or analyze events using CLI tool jfr print-events. 3. Inspect JFR event views for Java monitor blocked, file read and write and socket read latency events. 4. Trace the thread stack execution graph for threads experiencing the highest monitor lock wait times. Phase 3. Root cause analysis. 1. Evidence collected. JMC thread lock analysis revealed 50 worker threads blocked for 1.8 seconds on Java monitor, blocked waiting on logback.core.file appender. 2. Primary root cause. A legacy logback appender was configured with synchronous disk file writes immediate flush equals true, causing worker threads to block on disk I/O lock contention during peak transaction volume. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Switch to asynchronous logging, for example, logback async appender. Validate that log delivery requirements are still met and perform a rolling restart. 2. Permanent resolution. Standardize asynchronous, non-blocking logging configurations across all microservice-based templates. 3. Validation. Confirm zero Java monitor blocked events in subsequent JFR profiles. Verify P99 transaction latencies drop to 10 milliseconds, and monitor throughput. Phase 5. Recurrence prevention. 1. Configure continuous rolling JFR recording -XX: start flight recording in production-based images with a 15-minute disk repository buffer. 2. Mandate asynchronous logging appenders across all microservices using automated CI and CD linter checks. 3. Integrate JFR profiling analysis into staging performance regression test pipelines. Pro tip: interview insight. Java Flight Recorder JFR is built into the JDK and incurs less than 1% overhead in production. Use JCMD1 JFR. Start to capture high-fidelity event data thread lock contention, allocation hotspots, I/O directly in live production when APM tools fail.
Follow up when expected. A logical continuation of the incident. How does Java Flight Recorder, JFR, achieve extremely low overhead, less than 1% in production compared to traditional profilers?
Answer: JFR is integrated directly into the hotspot JVM kernel. It reads event buffers populated during standard JVM execution, such as thread state changes or safe points, without injecting bytecode or forcing thread unwinding, writing events asynchronously to ring buffers with under 1% CPU overhead.
Follow up deeper. Experienced tester. How do you configure continuous JFR recording with a rolling 15-minute disk repository buffer using -XX start flight recording in container startup arguments?
Answer: you configure -XX: start flight recording equals disk equals true comma dump on exit equals true comma max age equals 15 minutes comma settings equals profile in the container JVM startup options. This keeps a rolling 15-minute window of event data on disk at all times, allowing SREs to dump historical data JCMD_PID_JFR.dump immediately after an incident occurs.
Follow up 3 curveball. How do you analyze JFR event dumps using JDK Mission Control, JMC, or automated CLI tools, JFR print -- events, to extract thread lock contention and allocation flame graphs?
Answer: in JMC, navigate to the lock instances view to analyze monitor wait times, or memory view for allocation profiles and flame graphs when generated using supporting profiling tools. Using CLI tools, execute JFR print -- events jdk.java monitor wait file.jfr to extract raw text event logs, or convert JFR files to flame graphs using async profiler's converter.
Category 2 conclusion.
Mastering JVM memory management, garbage collection mechanics, and platform diagnostic tooling is what protects enterprise Java applications from catastrophic runtime crashes, latency spikes, and unexplainable outages. By configuring dynamic container memory percentages, conducting systematic heap dump dominator tree analysis, and setting explicit metaspace and code cache bounds, you build a stable, highly performant Java runtime ecosystem.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition from Category 2 JVM, Heap, GC and Java platform to Category 3 CPU, Threads and Concurrency.
While maintaining heap stability and avoiding memory leaks is critical, application availability is equally threatened when worker threads freeze or CPU capacity is exhausted. Thread deadlocks, synchronization bottlenecks, and unbounded execution pools can instantly halt transaction processing even on a perfectly healthy JVM heap. We now transition from memory and platform layers to thread execution and concurrency engineering. Category 3, CPU, Threads and Concurrency.
Category 3, CPU, Threads and Concurrency.
CPU, Threads and Concurrency incidents govern how parallel execution, thread pool limits, and synchronization constructs behave under high-throughput production workloads. This category deep dives into resolving 100% CPU spikes, thread deadlocks, thread pool exhaustion, redos regular expression backtracking, synchronization bottlenecks, infinite retry loops, thread local leaks, and virtual thread migration challenges in Java 21. Mastering these incidents ensures you can deliver a high-throughput, deadlock-free concurrency architecture.
Category 3. CPU, Threads, and Concurrency 37 to 51.
Here are the 15 CPU, thread execution, and concurrency incidents we will solve in this category. Incident 37. CPU reaches 100% without increased business traffic. Incident 38. Deadlocked threads freeze customer transactions completely. Incident 39. Thread pool exhaustion causes request queuing and HTTP 503 errors. Incident 40. External API blocks all worker threads due to missing I/O timeouts. Incident 41. Synchronization bottleneck degrades multi-pod scaled throughput. Incident 42. Infinite retry loops cause CPU saturation and log disk flooding. Incident 43. Excessive thread creation causes native thread allocation Incident 44. Long-running background jobs starve web request worker thread pools. Incident 45. Busy wait loops cause high CPU consumption in worker threads. Incident 46. Deadlock versus livelock versus starvation concurrency analysis. Incident 47. Thread local memory leaks retain user context in Tomcat worker threads. Incident 48. Hash map versus concurrent hash map corruption under concurrent rights. Incident 49. Fork join pool starvation blocks parallel stream processing. Incident 50. Virtual threads migration issues and pinned carrier threads in Java 21. Incident 51. Async completable future deadlocks caused by shared thread pool starvation. Total 15 CPU and concurrency incidents. Let's dive into Incident 37.
Production Incident 37. A production order calculation microservice suddenly spikes to 100% CPU utilization on all pod replicas without any increase in business transaction volume. API response times degrade from 20 milliseconds to over 10 seconds. As the on-call Java application support engineer, how do you investigate, resolve, and prevent this 100% CPU spike?
Answer: when CPU utilization reaches 100% without a corresponding increase in traffic, my priority is to isolate high-consuming thread IDs, capture thread dumps, and analyze execution stack traces using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check container CPU utilization metrics in Grafana to confirm 100% CPU saturation across pod replicas. 2. Verify request volume RPS in APM dashboards to confirm business transaction throughput remains flat. 3. Check pod readiness status using kubectl. Get pods to determine if CPU throttling is triggering probe timeouts. Phase 2. Investigation and evidence gathering. 1. Exec into the burning container kubectl exec and run top-h-p1 to locate the specific OS thread ID PID consuming 100% CPU. 2. Convert the decimal thread PID to hexadecimal using printf%x\npid. 3. Generate a JVM thread dump using jcmd1thread.print and search for the matching native thread ID NID equals 0x hex. 4. Inspect the execution stack trace for the identified thread to locate the exact Java method and line number running in a tight loop. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed thread HTTP neo 8080 exec 4 NID equals 0x1a3f in runnable state executing java.util.regex.pattern.match. 2. Primary root cause. Catastrophic regular expression backtracking redos. A newly deployed order discount rejects pattern executed an unbounded greedy quantifier against a malformed string payload, causing the regex engine to execute exponential evaluation steps. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Apply a temporary API gateway request payload filter blocking the malformed string pattern and perform a rolling restart using kubectl rollout restart to kill stuck threads. 2. Permanent resolution. Refactor the regular expression to use possessive quantifiers, for example, a++ or atomic groups open paren question mark greater than close paren where appropriate, and enforce string length limits. 3. Validation. Redeploy send synthetic test payloads and confirm container CPU usage returns to baseline 15% utilization. Phase 5. Recurrence prevention. 1. Implement static code analysis rules sonar quebef flagging vulnerable regular expressions prone to re-DOS backtracking. 2. Configure execution time limits on regex evaluations or use re2j non-backtracking regex engines. 3. Enforce mandatory CPU profiling using a sync profiler during pre-release load testing. Pro tip interview insight. To pinpoint a 100% CPU thread in 30 seconds, run top-h-p1 inside the container to get the decimal OS thread ID, convert it to hex using printf%xpid, and grep for that exact NID in a thread dump jcmd1 thread.print.
Follow-up when expected. A logical continuation of the incident. How do you map a decimal OS thread ID from top-h-p1 to a native thread ID, NID, in a Java thread dump?
Answer. Run top-h-p1 inside the container to identify the high CPU decimal thread ID, for example, 6719. Convert 6719 to hexadecimal using printf%x\n 6719, which gives 1A3F. In the JVM thread dump generated via jcmd1 thread.print, search for NID equals 0x1 a 3F to locate the exact Java thread stack trace.
Follow-up 2 deeper. Experienced tester. What is catastrophic regex backtracking re-DOS, and how do possessive quantifiers prevent CPU starvation?
Answer. Re-DOS occurs when a regular expression contains overlapping nested quantifiers such as a $+$. When evaluated against a non-matching string, NFA regex engines evaluate all possible branch combinations exponentially. Possessive quantifiers like A++ forbid the regex engine from relinquishing matched characters to retry sub-patterns, eliminating backtracking loops.
Follow-up 3 curveball. What if top-h shows that CPU usage is evenly distributed across 50 worker threads rather than a single rogue thread? How do you diagnose the bottleneck?
Answer. Even CPU distribution across many threads indicates high concurrent execution volume or garbage collection activity rather than a single infinite loop. I would run a sync profiler as prof-ec_d30-f/temp/cpu.html1 to generate a CPU flame graph, identifying which methods consume the highest aggregate CPU cycles across the entire thread pool.
Production Incident 38. An inventory management microservice freezes completely under concurrent traffic. New incoming HTTP requests hang until client timeouts occur. APM dashboards show 0 CPU activity, 100% blocked threads, and 0 transaction processing. As the on-call Java application support engineer, how do you resolve this thread deadlock outage?
Answer. When an application freezes with 0 CPU usage and blocked threads due to a Java deadlock, my priority is to generate a thread dump, locate circular monitor lock acquisitions, and restore transaction processing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check APM dashboards to confirm 0 CPU activity, accompanied by a 100% drop in transaction throughput. 2. Check pod status using kubectl, get pods to verify if readiness probes are timing out due to blocked worker threads. 3. Confirm whether the transaction freeze impacts all cluster pods or only specific instances under heavy concurrency. Phase 2. Investigation and evidence gathering. 1. Generate a JVM thread dump using jcmd1 thread.print or jstack1. 2. Scroll to the bottom of the thread dump file to review the automated JVM deadlock diagnostic section found one deadlock. 3. Analyze the circular lock dependency chain between thread states, monitor lock addresses, and owning thread IDs. 4. Inspect source code methods participating in the deadlock for nested synchronized blocks or lock acquisition order mismatches. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed thread 1 holding lock A waiting on lock B, while thread 2 held lock B waiting on lock A. 2. Primary root cause. Inconsistent lock acquisition order, inventory service.transfer acquired warehouse lock then item lock. whereas item service.update acquired item lock then warehouse lock, creating a classic circular wait deadlock under concurrent traffic. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling restart using kubectl rollout restart to terminate deadlocked threads and restore immediate inventory transaction processing. 2. Permanent resolution. Establish a consistent lock acquisition order across all services using reentrant lock.try lock with explicit timeouts where timeout semantics are appropriate. 3. Validation. Redeploy, execute concurrent inventory transfer load tests, and verify 0% thread deadlocks. Phase 5. Recurrence prevention. 1. Implement static code analysis rules sonar cube flagging nested synchronized blocks. 2. Mandate explicit timeout bounds on all lock acquisitions using reentrant lock instead of intrinsically synchronized methods. 3. Conduct high concurrency stress testing in staging to validate lock safety pre-release. Pro tip interview insight. JVM thread dumps automatically detect Java monitor deadlocks and append a found one deadlock summary at the bottom of the dump. Never use raw nested synchronized blocks without explicit timeout mechanisms. Always leverage reentrant lock.try lock with timeout to fail fast.
Follow up when expected. A logical continuation of the incident. How does the JVM automatically detect deadlocks during thread dump generation?
Answer. When jcmd1 thread.print is executed, the JVM builds an object monitor dependency graph. It traverses object lock ownership chains searching for cycles where thread A waits for thread B, which waits for thread A. If a cycle is detected, the JVM prints the found one deadlock summary listing the involved thread names and monitor addresses.
Follow up to deeper. Experienced tester. How does reentrant lock.try lock with timeout and time unit prevent permanent thread deadlocks compared to synchronized blocks?
Answer. Intrinsic synchronized blocks wait indefinitely for a monitor lock, keeping threads blocked forever during a deadlock. Reentrant lock.try lock attempts lock acquisition for a specified duration, for example, 5 seconds. If the lock cannot be acquired within the timeout, try lock returns false, allowing the thread to release its own locks and fail gracefully.
Follow up 3 curveball. What if a deadlock occurs on database connections, database-level deadlock, rather than Java object monitors? How does that manifest in JVM thread dumps?
Answer. A database deadlock does not trigger the JVM's found one deadlock Java monitor summary. In JVM thread dumps, application threads appear stuck in waiting or timed_waiting inside JDBC driver socket read methods, socket input stream.socket read 0. To diagnose, query database lock tables like pg_stat_activity or show engine in NoDB status.
Production Incident 39. A high-volume payment gateway microservice starts returning HTTP 503 service unavailable errors under peak load. Tomcat request processing threads reach their maximum capacity 200 threads, queuing requests until task rejected exception is thrown. As the on-call Java application support engineer, how do you resolve this thread pool exhaustion?
Answer. When worker thread pools become exhausted returning HTTP 503 errors, my priority is to inspect thread execution states, isolate slow downstream blocking calls, and apply circuit breakers using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM thread pool metrics to confirm Tomcat busy thread counts equal maximum pool size busy_threads is equal to 200. 2. Check HTTP response codes in Grafana to verify the rate of 503 service unavailable and task rejected exception errors. 3. Determine whether request queuing and thread exhaustion affect all pods or specific availability zones. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using jcmd1 thread.print to examine worker thread states. 2. Analyze stack traces for HTTP Neo 8080 exec threads to determine why worker threads are stuck in waiting or timed_waiting state. 3. Check downstream external API dependency latency in APM transaction maps. 4. Review embedded Tomcat thread pool settings in application.yml server.tomcat.threads.max. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump revealed 195 Tomcat exec threads blocked in socket input stream. Socket read 0 executing HTTP calls to a third-party fraud verification API. 2. Primary root cause. Upstream slow dependency. A third-party fraud verification API experienced response latency spikes, causing all Tomcat worker threads to block waiting for I/O and exhausting the 200-thread pool. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Apply a resilience 4J circuit breaker on the fraud verification API client to fail fast on slow calls and perform a rolling restart to free exhausted Tomcat threads. 2. Permanent resolution. Configure explicit socket read timeouts on the fraud verification HTTP client and refactor calls to use non-blocking asynchronous web client executions. 3. Validation. Confirm Tomcat busy thread count drops to baseline 25 threads, HTTP 503 errors disappear, and payment API latencies normalize. Phase 5. Recurrence prevention. 1. Enforce mandatory resilience 4J circuit breakers and bulkhead isolation patterns on all third-party HTTP integrations. 2. Configure Prometheus alerts for Tomcat busy thread utilization exceeding 80% of max pool size. 3. Standardize asynchronous, non-blocking HTTP client configurations across all microservice archetype templates. Pro tip interview insight. Thread pool exhaustion is almost never fixed by simply increasing max thread count. Adding more threads increases context switching overhead and memory consumption. Always apply bulkhead isolation and circuit breakers on external API callers so slow downstream dependencies cannot exhaust your container's worker thread pool.
Follow up when expected. A logical continuation of the incident. Why is increasing server.tomcat.threads.max from 200 to 1000 usually a bad solution for thread pool exhaustion?
Answer. Increasing max threads on a block dependency simply allows more threads to become stuck. With a 1 megabyte stack size, roughly 1,000 Java threads consume about 1 gigabyte of native stack memory -XS-S1M and create severe OSCPU context switching overhead, worsening overall system throughput instead of restoring performance.
Follow up 2 deeper. Experienced tester. How does the Resilience 4J bulkhead pattern protect worker thread pools from downstream dependency latency?
Answer. Bulkhead limits the maximum number of concurrent requests allowed to execute against a specific downstream service, for example, capping fraud API calls to 20 threads. If those 20 threads block, Bulkhead rejects additional calls instantly, preserving the remaining 180 Tomcat threads for unrelated payment APIs.
Follow up 3 curveball. What if a thread pool queue is configured with integer.max value capacity? How does that affect application latency and out-of-memory error risk?
Answer. An unbounded task queue integer.max value causes thread pool executor to never spawn threads beyond core pool size, queuing millions of tasks indefinitely. This causes extreme request latency, stale data processing, and eventually exhausts Java heap memory, throwing out-of-memory error.
Production Incident 40. An e-commerce fulfillment microservice experiences a complete freeze across all pods. Investigation reveals a third-party shipping provider API experienced network latency, causing all Spring at async and Tomcat execution worker threads to block waiting for I/O. As the on-call Java application support engineer, how do you resolve this blocking I/O outage?
Answer. When untimed external API calls block all container worker threads, my priority is to inject mandatory socket timeouts, isolate HTTP client beans, and restore thread availability using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check a PM transaction dependency maps to identify latency spikes on external HTTP shipping API calls. 2. Inspect pod status using kubectl, get pods to verify if readiness probes are failing due to worker thread starvation. 3. Confirm whether the worker thread freeze affects all microservice operations or specific shipping workflows. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using JCMD oneThread.print. 2. Analyze stack traces for worker threads stuck in socket input stream.socket read 0 or HTTP client.send. 3. Inspect Spring configuration for REST template or HTTP client bean definitions to check timeout settings. 4. Verify whether default HTTP client auto configurations lack explicit connect timeout and read timeout values. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 180 worker threads stuck in socket read 0 executing REST template.exchange. 2. Primary root cause. Missing socket timeouts. The REST template bean was instantiated using default configurations without connect timeout or read timeout, causing worker threads to block indefinitely when the external shipping API dropped TCP packets. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Inject explicit socket timeouts connect timeout equals 2 seconds. Read timeout equals 5 seconds into the HTTP client bean via config map update or hotfix and perform a rolling restart. 2. Permanent resolution. Replace blocking REST template calls with non-blocking web client or wrap invocations in Resilience for JTime limiter instances. 3. Validation. Confirm worker threads clear from socket read 0, API latencies return to normal, and fulfillment processing resumes. Phase 5. Recurrence prevention. 1. Enforce global HTTP client auto configurations that inject mandatory socket timeouts across all microservices. 2. Implement chaos engineering tests injecting network latency in staging environments to validate timeout behavior. 3. Establish APM alerts monitoring external dependency response times exceeding 3 seconds. Pro tip interview insight. Timeout defaults vary by HTTP client implementation. Always configure explicit connect, read, and connection acquisition timeouts instead of relying on defaults. Untimed socket reads block worker threads forever if a remote server drops TCP packets, causing worker thread starvation.
Follow up when expected. A logical continuation of the incident. What is the difference between connect timeout and read timeout in Java HTTP clients?
Answer. Connect timeout specifies the maximum time allowed to establish the initial TCP handshake with the remote server. Read timeout socket timeout specifies the maximum time allowed between receiving consecutive data packets after the connection is established.
Follow up 2 deeper. Experience tester. Why does Spring Web Client handle downstream API latency better than blocking REST template under high concurrency?
Answer. REST template uses a thread per request model, holding an entire OS worker thread blocked during I/O socket reads. Web client uses non-blocking netty event loops. When a request is sent, the event loop thread is freed immediately to handle other requests, resuming processing only when a network event notification arrives.
Follow up 3 curveball. What if an external API call is configured with a 3-second read timeout, but under load, the client thread remains blocked for 30 seconds before throwing socket timeout exception?
Answer. This occurs when DNS resolution hangs or connection pool acquisition blocks before the HTTP socket is opened. Read timeouts only apply after a connection is established. To fix, configure explicit DNS lookup timeouts and connection pool lease timeouts connection timeout on the HTTP client pool.
Production Incident 41. After expanding pod replicas from 2 to 10 to handle a Black Friday flash sale, application throughput drops by 60% and transaction latencies skyrocket. Thread dumps reveal hundreds of worker threads in blocked state waiting to enter a synchronized method inside a singleton Spring bean. As the on-call Java application support engineer, how do you resolve this synchronization bottleneck?
Answer. When horizontal scaling degrades throughput due to monitor lock contention, my priority is to identify the owning thread, replace synchronized blocks with lock-free atomic constructs, and restore parallel processing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics to confirm throughput RPS dropped 60% despite scaling pods from 2 to 10. 2. Check container CPU utilization in Grafana to verify CPU usage is unexpectedly low while request latencies spike. 3. Verify thread states using APM thread distribution charts to confirm high blocked thread counts. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using JCMD1thread.print. 2. Search for worker threads in blocked on object monitor state. 3. Trace the monitor lock address waiting to lock 0x00000071234567 back to the owning thread locked 0x0000000712345678. 4. Inspect source code for synchronized keywords on singleton Spring Bean methods or shared static objects. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 190 HTTP Neo 808 0 exec threads blocked waiting on object monitor 0x0000000712345678 held by thread exec 12. 2. Primary root cause. Critical section lock contention. A core sequence generator method in a singleton Spring Bean was annotated with synchronized, forcing concurrent worker threads to execute serially through a single thread bottleneck. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Deploy an emergency hotfix replacing the synchronized method with non-blocking lock-free atomic long or long adder constructs and perform a rolling restart. 2. Permanent resolution. Redesign sequence generation to use lock-free atomic variables or distributed RIDIs or database sequence generators when global ordering across instances is required. 3. Validation. Confirm blocked thread count drops to 0, transaction throughput scales linearly with pod counts and latencies normalize. Phase 5. Recurrence prevention. 1. Enforce static code analysis rules SonarQube prohibiting synchronized keywords on singleton Spring Bean methods. 2. Conduct mandatory multi-thread contention profiling using a sync profiler during pre-release stress testing. 3. Standardize lock-free concurrent data structures across all high-throughput microservice codebases. Pro tip interview insight. The synchronized keyword enforces single-threaded serial execution across all worker threads contending for that lock. In high-throughput microservices, replace synchronized blocks with lock-free atomic constructs, such as atomic long or concurrent hash map, to allow non-blocking parallel execution.
Follow up when expected. A logical continuation of the incident. Why does atomic long or long adder outperform synchronized blocks under heavy thread contention?
Answer. Synchronized blocks suspend blocked threads at the OS level, incurring severe context switching overhead. Atomic long uses hardware-level CAS compare and swap CPU instructions to update memory without thread suspension. Long adder goes further by maintaining cell arrays per thread, avoiding CAS contention under extreme concurrency.
Follow up deeper. Experienced tester. What is thread contention, and how do you measure monitor lock wait times in APM or JFR?
Answer. Thread contention occurs when multiple threads compete simultaneously for the same monitor lock. In JFR Java Flight Recorder, view Java Monitor blocked events in JDK Mission Control to measure total lock wait duration and identify the exact class and method causing the lock bottleneck.
Follow up 3 curveball. What if replacing synchronized with reentrant lock improves throughput slightly, but threads still experience lock wait delays? How do you optimize further?
Answer. I would reduce lock granularity. Instead of locking the entire method or map, use read-write lock allowing concurrent reads while locking writes or stamped lock, or partition data, using concurrent hash map segment hashing so threads lock separate data buckets independently.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 42. A message consumer microservice experiences 100% CPU utilization and floods Splunk with millions of error logs per minute. Investigation reveals a single unparsable poison pill message in RabbitMQ triggers an infinite, immediate retry loop. As the on-call Java application support engineer, how do you resolve this infinite retry loop outage?
Answer: when an unhandled poison pill message triggers infinite retry loops and CPU saturation, my priority is to isolate the poison message, route it to a dead letter queue, and configure exponential backoff using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Splunk or ELK dashboards for rapid log volume spikes and repeating consumer exception traces. 2. Check container CPU utilization using kubectl top pods to confirm 100% CPU saturation on consumer pods. 3. Identify the specific RabbitMQ or Kafka consumer queue experiencing rapid message redelivery. Phase 2. Investigation and evidence gathering. 1. Inspect application consumer logs for repeating JSON parse exception or illegal argument exception stack traces. 2. Review Spring AMQP or Kafka listener error handler configuration in application.yml for missing retry backoff settings. 3. Check RabbitMQ Management Console or Kafka Consumer Group lag to locate the stuck poison pill message payload. Phase 3. Root cause analysis. 1. Evidence collected. Splunk logs showed 50,000 JSON parse exception errors per second on order consumer.process. 2. Primary root cause. Missing retry backoff in DLQ. The Spring AMQP listener container was configured with immediate retry without exponential backoff or max attempt bounds, causing the consumer thread to reprocess the same poison message thousands of times per second. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Manually move the poison pill message to a dead letter queue DLQ via Management Console to clear the loop and perform a rolling restart. 2. Permanent resolution. Configure exponential backoff with appropriate initial interval, multiplier, and maximum interval parameters, and set max attempts equals 3 with automatic DLQ routing. 3. Validation. Confirm consumer CPU usage drops to baseline 10%, log flooding halts, and valid messages process normally. Phase 5. Recurrence prevention. 1. Mandate standardized error handler templates with exponential backoff and DLQ routing across all message consumer microservices. 2. Configure Splunk or ELK log volume alerts to detect log floods within 1 minute. 3. Implement strict JSON schema validation on incoming message listeners to catch malformed payloads pre-processing. Pro tip interview insight. Never configure message consumers with infinite immediate retry loops. Always enforce exponential backoff with a maximum retry limit such as 3 attempts, and route unprocessable poison pill messages to a dead letter queue DLQ to prevent 100% CPU saturation and log disk flooding.
Follow up when expected. A logical continuation of the incident. How does exponential backoff with jitter prevent retry storms in message consumers and microservices?
Answer. Exponential backoff increases wait times exponentially between retries 1 second, 2 seconds, 4 seconds, 8 seconds, giving downstream systems time to recover. Adding random jitter variants prevents synchronized retry storms where thousands of concurrent clients retry at the exact same millisecond interval.
Follow up deeper. Experienced tester. What is a dead letter queue DLQ or dead letter topic DLT, and how do you safely reprocess poison messages after fixing code?
Answer. A DLQ or DLT is a dedicated secondary queue where unprocessable messages are routed after exhausting retry attempts. Once the application bug is fixed or schema updated, a DLQ replay tool or consumer task reads messages from the DLQ and re-injects them into the main processing queue.
Follow up 3 curveball. What if a poison message causes an out-of-memory error during deserialization before the Spring error handler can catch it or route it to a DLQ?
Answer. If payload deserialization exhausts heap memory causing the JVM crashes or container terminates before error handlers execute. Upon restart, the consumer fetches the same message, creating a crash loop back off. To fix, enforce maximum payload size limits at the broker level, for example, max.message.bytes, and configure streaming JSON parsers.
Production Incident 43. A Java batch application running inside Docker crashes with java.lang. Out-of-memory error, unable to create new native thread. Linux host metrics show the process attempted to spawn over 10,000 OS threads before exceeding kernel limits. As the on-call Java application support engineer, how do you resolve this native thread allocation outage?
Answer. When an application crashes with unable to create new native thread, my priority is to inspect thread creation sources, replace unmanaged thread spawns with bounded thread pools, and adjust OS limits using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application crash logs using kubectl logs to confirm java.lang. Out of memory error, unable to create new native thread. 2. Check process thread counts on the host using pstree-ppid pipe wc-l or ls/proc/pid/task pipe wc-l. 3. Verify operating system ulimit-umax user processes limits on worker nodes. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using jcmd1thread.print to analyze active thread names and stack trace creation origins. 2. Review source code for manual new thread.start instantiations inside request processing loops. 3. Check thread stack size configurations -xss in JVM startup arguments. 4. Verify whether third-party libraries or unbounded executor services spawn uncapped threads. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 9,800 active threads named thread 1 through thread 9,800 executing file import task. 2. Primary root cause. Unbounded thread creation. A file import task spawned new thread with task.start inside a loop for every record in a 10,000-row file, exhausting kernel ulimit limits, and throwing native thread Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Increase thread or process limits ulimit-u only after confirming sufficient native memory remains available and identifying the source of excessive thread creation. Then perform a rolling restart. 2. Permanent resolution. Refactor code to replace manual new thread calls with a bounded thread pool executors.new fixed thread pool with 20. 3. Validation. Confirm thread counts remain capped at 20 worker threads during file imports and verify batch processing completes. Phase 5. Recurrence prevention. 1. Enforce static code analysis rules sonar cube flagging direct new thread instantiations. 2. Configure thread stack size explicitly -xss 512K to reduce native memory consumption per thread. 3. Mandate bounded thread pool task executor bean definition across all microservice batch tasks. Pro tip interview insight. Each Java thread requires native OS thread stack memory default 1 MB via -xss. Spawning threads manually via new thread.start inside loops will rapidly exhaust kernel thread limits ulimit and native memory. Always use managed, bounded thread pool executors.
Follow up when expected. A logical continuation of the incident. How does -xss thread stack size impact maximum thread creation capacity on 64-bit Linux systems?
Answer. -xss sets native memory allocated for each thread stack default 1024 kilobytes or 1 megabyte on 64-bit Linux. 1,000 threads consume 1 gigabyte of off-heap native RAM. Reducing -xss 512 kilobytes cuts thread stack memory in half, allowing double the thread capacity within the same OS native memory footprint.
Follow up 2 deeper. Experience tester. What operating system kernel limits ulimit/max_map_count restrict thread creation in Docker and Kubernetes containers?
Answer. Linux kernel enforces ulimit-umax user processes /threads per user ID and sysctl kernel.pid_max global max PIDs. In containers, cgroup PIDs.max restricts total threads allowed inside the container cgroup. Reaching any of these limits causes unable to create new native thread.
Follow up 3 curveball. What if a thread dump reveals thousands of threads named pool 1 thread, X stuck in timed_waiting? What causes this thread pool leak?
Answer. This occurs when application code repeatedly instantiates executors.new fixed thread pool inside a request scoped method, instead of reusing a single shared thread pool executor bean. Each method call creates a new thread pool that remains active in memory, leaking threads until OS limits are exhausted.
Production Incident 44. An analytics microservice experiences progressive API latency degradation over business hours. APM dashboards reveal that long-running background report generation tasks executed via at a sync run on the same shared thread pool as incoming web requests, starving HTTP worker threads. As the on-call Java application support engineer, how do you resolve this thread starvation?
Answer: when long-running background jobs starve web request worker threads, my priority is to inspect thread pool execution policies, enforce thread pool bulkheading, and isolate batch execution using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM transaction traces to verify whether HTTP API requests share thread pool executors with background at async report jobs. 2. Check HTTP P99 response times in Grafana to confirm latency degradation correlates with background report triggers. 3. Verify whether worker thread starvation affects all service replicas or only specific nodes. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using JCMD1thread.print. 2. Analyze stack traces for worker threads named Task 1, Task 2 to check if background report tasks occupy all task executor threads. 3. Review Spring configuration for missing custom task executor bean definitions. 4. Check if at-async methods default to Spring's unbounded simple async task executor. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 100 worker threads in simple async task executor running heavy PDF generation tasks, consuming all available CPU and thread execution slots. 2. Primary root cause. Thread pool contamination. The application used Spring's default at-async executor simple async task executor, which creates a new thread per task without pooling. Excessive background thread creation competes with Tomcat worker threads for CPU and system resources. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Define a dedicated bounded thread pool task executor report executor for background jobs with lower thread priority and perform a rolling restart. 2. Permanent resolution. Annotate background report methods explicitly with at-async report executor to isolate background task threads from HTTP web request pools. 3. Validation. Confirm HTTP API IP99 latencies return to 15 milliseconds. Verify Tomcat busy threads remain low during report generation, and monitor throughput. Phase 5. Recurrence prevention. 1. Mandate custom, named thread pool task executor bean definitions for all at-async methods across microservice repositories. 2. Configure bulkhead isolation patterns to decouple web API execution tiers from background processing tiers. 3. Establish architectural separation by offloading heavy batch jobs to dedicated worker microservices. Pro tip interview insight. By default, Spring's at-async uses simple async task executor which does not reuse threads and creates new unbounded threads for every invocation. Always configure dedicated, named thread pool task executors for background tasks to isolate heavy batch jobs from user-facing HTTP request thread pools.
Follow-up when expected. A logical continuation of the incident. Why is Spring's default simple async task executor dangerous for production at-async methods?
Answer: simple async task executor does not pool or reuse threads. Every single at-async method invocation spawns a brand new unmanaged Java thread. Under high concurrency, this causes unbounded thread creation, severe CPU context switching overhead, and native thread crashes.
Follow-up to deeper. Experienced tester. How do you configure a thread pool task executor with core pool size, max pool size, and queue capacity in Spring Boot?
Answer: define at bean returning thread pool task executor. Set core pool size minimum active threads, max pool size maximum threads spawned under queue saturation, queue capacity task queue limit before spawning max threads, and specify a rejected execution handler such as caller runs policy or abort policy.
Follow-up 3 curveball. What if an at-async background task throws an unhandled runtime exception? How does Spring handle the exception, and how do you capture it for logging?
Answer: for void at-async methods, unhandled exceptions cannot propagate back to the caller thread and are logged as uncaught exceptions by default. To handle them, implement Spring's async uncaught exception handler interface in an at-configuration class, implementing async configurer to log exception context and trigger alerts.
Production Incident 45. A custom queue-polar microservice exhibits 100% CPU utilization on single worker threads. Investigation reveals that worker threads spin continuously in a while-not-ready loop without sleeping, yielding, or waiting on a monitor condition, starving other tasks. As the on-call Java application support engineer, how do you resolve this busy wait loop outage?
Answer: when a busy wait loop consumes 100% CPU cycles spinning without yielding, my priority is to isolate the polling thread, replace busy spinning with blocking queue operations, and restore CPU headroom using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check container CPU utilization in Grafana to confirm 100% CPU saturation on worker thread cores. 2. Check APM transaction metrics to verify if overall business request processing throughput remains low despite high CPU load. 3. Verify pod status using kubectl get pods to check if CPU throttling triggers readiness probe failures. Phase 2. Investigation and evidence gathering. 1. Exec into the container kubectl exec and run top-h-p1 to identify the high CPU decimal thread ID. 2. Convert the decimal thread PID to hexadecimal using printf%x\npid. 3. Generate a JVM thread dump using jcmd1thread.print and locate the matching native thread ID NID equals 0x hex. 4. Inspect the thread stack trace to locate the type while loop executing without sleep or wait invocations. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed thread queuepolar 1 NID equals 0x2b4c in runnable state, constantly executing custom queue.poll inside a tight while loop. 2. Primary root cause. Busy wait spinning. A custom queuepolar was implemented as a spin loop instead of using blocking synchronization primitives such as blocking queue.take, condition.await, or an appropriate parking strategy, lock support.park nanos, where polling is unavoidable, consuming 100% CPU cycles on a single core doing zero useful work. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart and deploy an emergency patch adding thread.sleep with 10 to the polling loop to restore immediate CPU capacity. 2. Permanent resolution. Refactor the custom queue implementation to use array blocking queue.take or condition variables lock.new condition so worker threads block until messages arrive. 3. Validation. Confirm container CPU utilization drops from 100% to baseline 5% and verify message processing resumes. Phase 5. Recurrence prevention. 1. Implement static code analysis rules sonar cube flagging empty while loops or spin waits without sleep or wait calls. 2. Conduct mandatory CPU profiling using a sync profiler during pre-release staging load tests. 3. Enforce standard Java concurrency utilities blocking queue completable future across all event processing codebases. Pro tip interview insight. Busy wait loops spinning in a while loop without sleeping or waiting on a condition consume 100% CPU on an execution core doing zero useful work. Always replace custom polling loops with blocking queues like blocking queue.take or condition variables lock.new condition.
Follow up when expected. A logical continuation of the incident. Why is lock support.park nanos or thread.sleep preferred over an empty while loop when polling non-blocking resources?
Answer: an empty while loop spins continuously on the CPU, executing billions of useless instructions per second. Lock support.park nanos or thread.sleep deschedules the worker thread at the OS kernel level, freeing the CPU core to execute other active threads until the timer expires or an unparked signal arrives.
Follow up 2 deeper. Experience tester. How does java.util.concurrent.array blocking queue eliminate busy wait loops in producer-consumer workflows?
Answer: array blocking queue.take uses reentrant lock condition variables not empty.await. When the queue is empty, consumer threads enter a waiting state and yield their CPU core. When a producer thread inserts an item via put, it signals not empty.signal, waking up a consumer thread instantly without spin wait overhead.
Follow-up 3 curveball. What if a spin wait loop is required for ultra-low latency financial trading under 1 microsecond? How do you implement a safe spin loop in Java 9 Plus without damaging CPU hardware?
Answer: in ultra-low latency sub-microsecond trading, thread context switching overhead is unacceptable. Java 9 introduced thread dot on spin wait, which issues a native CPU hardware hint such as the x86 pause instruction. This optimizes processor pipeline power consumption and prevents memory bus lockup during short spin wait loops.
Production Incident 46. During high concurrency order processing, threads in a payment settlement engine degrade into 3 distinct failure modes. Some threads freeze permanently, others consume 100% CPU, constantly changing state without making progress, while background auditing threads experience indefinite postponement because higher priority threads repeatedly obtain the lock. As the on-call Java application support engineer, how do you diagnose and resolve these concurrency failures?
Answer: when high concurrency workloads trigger deadlocks, live locks, or starvation, my priority is to analyze thread dumps over time, differentiate thread execution states, and apply fair lock policies using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics to observe mixed CPU behavior, where some pod replicas show 0% CPU deadlock, while others show 100% CPU live lock. 2. Check transaction processing rates in Grafana to verify complete stalls on specific order processing queues. 3. Confirm whether worker thread stalls trigger API gateway connection timeouts. Phase 2. Investigation and evidence gathering. 1. Capture 3 consecutive JVM thread dumps JCMD1 thread dot print space 10 seconds apart. 2. Compare thread state transitions across dumps. Identify blocked threads on circular monitors deadlock, runnable threads constantly changing stack frames inside retry loops live lock, or waiting threads starved of lock allocation. 3. Review source code for non-blocking try-lock retries lacking exponential backoff or jitter. 4. Check lock fairness settings on reentrant lock instances powering background auditing tasks. Phase 3. Root cause analysis. 1. Evidence collected. Thread dumps showed deadlocks on circular monitors, live locks on try-lock retries rapidly executing without backoff, and starvation on unfair reentrant lock with false instances. 2. Primary root cause. Multi-concurrency failure. Deadlocks caused by inconsistent lock acquisition order. Live locks caused by synchronized try-lock retries spinning without backoff, and starvation caused by high-priority transaction threads continually preempting auditing threads on unfair locks. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to clear deadlocked and live locked threads and restore processing capacity. 2. Permanent resolution. Enforce uniform lock acquisition ordering, add randomized exponential backoff and jitter to try-lock retries, and configure fair lock policies new reentrant lock with true for background auditing threads. 3. Validation. Confirm 0% deadlocks, CPU usage normalizes to 20% and background auditing tasks execute predictably. Phase 5. Recurrence prevention. 1. Mandate architectural concurrency reviews for all multi-lock or non-blocking retry algorithms. 2. Enforce randomized backoff requirements across all lock retry implementations in production code. 3. Conduct high concurrency contention profiling using Java Flight Recorder (JFR) in staging. Pro tip: interview insight. In thread dumps, deadlock shows threads permanently blocked waiting for each other. Live lock shows threads continuously runnable actively changing state without making business progress. Starvation shows threads stuck in waiting because higher priority threads continually preempt lock access.
Follow-up when expected. A logical continuation of the incident. How do you differentiate between deadlock, live lock, and thread starvation when inspecting consecutive Java thread dumps?
Answer: in consecutive thread dumps, deadlocked threads remain permanently in blocked state at the exact same monitor address. Live-locked threads remain in runnable state with stack frames changing rapidly inside retry loops. Starved threads experience indefinite postponement in waiting or timed underscore waiting states, because higher priority or continuously successful threads repeatedly obtain the lock.
Follow up 2 deeper. Experienced tester. Why does adding randomized jitter to non-blocking try-lock retry loops break live lock conditions?
Answer: live lock occurs when 2 or more threads attempt to acquire locks, fail, release their own locks, and retry at the exact same deterministic time interval, repeatedly colliding. Adding randomized jitter random time delay desynchronizes the retry attempts, allowing one thread to acquire both locks while the other waits.
Follow up 3 curveball. What is the performance trade-off of setting reentrant lock with true to enforce fair lock ordering across high-throughput microservices?
Answer: fair locks reentrant lock with true enforce a FIFO first in, first out queue for waiting threads, eliminating thread starvation. However, the trade-off is significantly lower throughput and higher CPU context switching overhead, because the JVM cannot grant locks to currently active running threads barging, forcing thread suspension and wake-up cycles.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 47. A multi-tenant Spring Boot microservice exhibits a gradual heap memory leak and severe cross-tenant data corruption. Investigation reveals customer users occasionally see tenant context data belonging to a previous HTTP request. As the on-call Java application support engineer, how do you resolve this thread local leak?
Answer: when thread local variables leak memory and cause cross-tenant data corruption on pooled web threads, my priority is to inspect web filter cleanup logic, enforce thread local remove and finally blocks, and purge pooled thread contexts using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check security audit logs to confirm reports of cross-tenant data bleeding during HTTP user transactions. 2. Inspect APM heap memory trends in Grafana to verify gradual memory accumulation across Tomcat worker threads. 3. Confirm whether tenant context corruption affects all web nodes or specific long-running pod instances. Phase 2. Investigation and evidence gathering. 1. Generate a production heap dump using jcmd1gc.heap_dump/temp/heap.hprof. 2. Load the heap dump into Eclipse MAT and inspect thread local map objects attached to Tomcat worker threads HTTP Neo 8080 exec. 3. Review custom Spring Web filters or handler interceptors for thread local set operations lacking thread local remove calls. 4. Verify whether unhandled exceptions in controller logic bypass context cleanup blocks. Phase 3. Root cause analysis. 1. Evidence collected. MAT heap dump analysis showed thousands of tenant context objects held inside thread local map instances attached to Tomcat worker threads. 2. Primary root cause. Thread local leak and data corruption. A custom tenant security filter invoked tenant context holder set with tenant ID on incoming HTTP requests, but failed to invoke tenant context holder remove in a finally block, causing stale tenant context objects to remain anchored to reusable pooled Tomcat threads. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling restart using kubectl rollout restart to flush pooled worker thread states and instantly eliminate active cross-tenant context corruption. 2. Permanent resolution. Wrap all thread local set operations inside try finally blocks that strictly invoke thread local remove in the finally clause, or migrate to Spring handler interceptor after completion. 3. Validation. Redeploy, execute multi-tenant synthetic load tests, verify 0% cross-tenant data leaks, and confirm heap baselines remain flat. Phase 5. Recurrence prevention. 1. Enforce static code analysis rules sonar cube flagging thread local set calls without a corresponding remove in finally blocks. 2. Implement mandatory web filter test suites asserting thread local cleanup post-execution. 3. Adopt Java 21 scoped values for request scoped context propagation where applicable. Pro tip interview insight. Web servers like Tomcat reuse worker threads across multiple HTTP requests. If you store data in a thread local without calling thread local remove in a finally block, that object stays attached to the pooled thread forever, causing memory leaks and dangerous cross-tenant data corruption.
Follow up when expected. A logical continuation of the incident. Why do thread local variables cause memory leaks in thread-pooled environments like Tomcat, even if the web request completes?
Answer: Tomcat worker threads are long-lived pooled objects. A thread local holds a strong entry inside the thread's internal thread local map. If remove is never called, the entry remains referenced by the living thread pool worker indefinitely, preventing garbage collection of the stored object graph long after the HTTP request finishes.
Follow up 2 deeper. Experienced tester. How do weak references inside thread local map work, and why can thread local keys be garbage collected while the value object leaks?
Answer. Thread local map uses weak reference wrappers for its keys, but strong references for its values. If the thread local key variable loses external strong references, GC reclaims the key, turning the map key to null. However, the value object remains strongly referenced by the pooled thread, causing an orphan value leak until the map is written to again or remove is called.
Follow up 3 curveball. How do Java 21 scoped value eliminate thread local memory leaks and cross-tenant data corruption in modern Java architectures?
Answer. Scoped value variables are immutable and bounded strictly to an explicit execution scope using scoped value where run. When the bounded code block finishes, the scoped value is automatically unbound and cleaned up by the JVM, preventing accidental object retention, thread pollution, or data corruption across pooled threads.
Production Incident 48. Under high concurrent customer traffic, a shared session tracking microservice spikes to 100% CPU utilization, hangs worker threads, and sporadically throws null pointer exceptions. Thread dumps reveal multiple worker threads executing inside java.util.hashmap.put. As the on-call Java application support engineer, how do you resolve this hashmap corruption?
Answer. When a non-thread safe hash map corrupts under concurrent writes causing 100% CPU loops, my priority is to inspect thread execution stacks, replace non-thread safe maps with concurrent hash map, and restore processing capacity using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check container CPU utilization in Grafana to confirm 100% CPU spikes across microservice pod replicas. 2. Inspect application logs using kubectl logs for unexpected null pointer exceptions or missing session keys. 3. Confirm whether thread hangs affect all request processing paths or specific session tracking endpoints. Phase 2. Investigation and evidence gathering. 1. Generate a JVM thread dump using jcmd1thread.print. 2. Search for multiple worker threads in runnable state stuck inside java.util.hashmap.put, hashmap.get, or hashmap.resize. 3. Inspect Spring Singleton Bean source code for shared static or instance hash map variables modified concurrently across HTTP request threads. 4. Verify whether map operations were wrapped in external synchronization blocks. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 12 HTTP Neo 8080 exec threads runnable at java.util.hashmap.put line 462 consuming 100% CPU. 2. Primary root cause. Hash map concurrent write corruption. A standard non-thread safe java.util.hashmap stored inside a singleton Spring service was modified concurrently by multiple HTTP request threads, causing structural corruption, inconsistent reads, lost updates, and potentially non-terminating traversal of corrupted bucket structures. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to terminate stuck CPU loop threads and restore immediate session processing. 2. Permanent resolution. Replace the standard hash map with a thread-safe concurrent hash map across all shared service components. 3. Validation. Confirm container CPU drops to baseline 10%. Null pointer exceptions cease, and high concurrency session tests pass. Phase 5. Recurrence prevention. 1. Enforce static code analysis rules SonarQube or find bugs banning non-thread safe collections hash map, array list in singleton Spring Beans. 2. Conduct high concurrency stress testing and staging to detect thread safety violations pre-release. 3. Standardize atomic concurrent data structures concurrent hash map. Copy on write array list across all shared microservice components. Pro tip interview insight. Standard java.util.hashmap is not thread-safe. Modifying a hash map concurrently across multiple threads causes structural corruption, inconsistent reads, lost updates, and unexpected runtime exceptions. Always use concurrent hash map for shared multi-threaded maps.
Follow up when expected. A logical continuation of the incident. How does concurrent hash map achieve high concurrency thread safety without locking the entire map like collections.synchronized map?
Answer: collections.synchronized map locks the entire map on every operation, forcing single-threaded access. Concurrent hash map uses fine-grained bucket level locking synchronized on individual bucket nodes in Java 8+ and lock-free CAS compare and swap operations for insertions, allowing thousands of threads to read and write different buckets simultaneously.
Follow up two deeper. Experienced tester. Why can concurrent hash map dot put if absent prevent race conditions that occur when using contains key followed by put?
Answer: executing if not map dot contains key with key map dot put with key value creates a non-atomic check, then act race condition, where another thread can insert a value between the contains key check and the put operation. Put if absent executes the check and insertion atomically inside the map, guaranteeing thread-safe single insertion.
Follow up three curveball. Does concurrent hash map allow null keys or null values? And why does attempting map dot put with key null throw null pointer exception?
Answer: concurrent hash map intentionally forbids null keys and null values, throwing null pointer exception. This design decision prevents ambiguity in concurrent environments where map.get with key returning null could mean either the key is absent or the key is mapped to null, which cannot be resolved safely without atomic locking.
Production Incident 49. A batch processing application utilizing Java parallel streams parallel stream experiences complete execution stalls. All parallel stream tasks across unrelated microservice workflows freeze, and API response times degrade sharply. As the on-call Java application support engineer, how do you resolve this fork join pool starvation?
Answer: when blocking I/O inside parallel streams starve the shared JVM common fork join pool, my priority is to inspect thread stack traces, isolate blocking I/O to custom thread pools, and restore parallel stream execution using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM transaction traces to confirm widespread execution stalls across parallel stream workflows. 2. Check thread pool metrics in Grafana to verify fork join pool.common pool worker thread saturation. 3. Confirm whether parallel stream freezes affect all application operations or specific batch tasks. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using JCMD oneThread.print. 2. Analyze stack traces for common pool worker threads fork join pool.common pool worker. 3. Identify if worker threads are stuck in socket input stream.socket read 0 executing blocking HTTP or database queries inside parallel stream lambdas. 4. Inspect source code for parallel stream.map operations executing synchronous network calls. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump revealed all 8 common pool worker threads stuck in socket read 0 executing REST template.get for object. 2. Primary root cause. Shared common pool starvation. A developer executed blocking HTTP I/O calls inside a parallel stream.map operation, occupying all worker threads in Java's shared JVM wide fork join pool.common pool, and starving all parallel streams across the application. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to free the common pool and disable the blocking parallel stream batch job. 2. Permanent resolution. Refactor parallel stream logic to execute blocking I/O inside a dedicated custom fork join pool instance new fork join pool with 16.submit or switch to completable future with dedicated thread pools. 3. Validation. Confirm common pool worker threads remain free, parallel stream batch processing completes, and API latencies normalize. Phase 5. Recurrence prevention. 1. Enforce architectural coding guidelines prohibiting blocking I/O or network calls inside Java parallel streams. 2. Mandate dedicated thread pool definitions for all high concurrency batch processing tasks. 3. Implement static analysis rules flagging network or database calls inside parallel streams. Pro tip interview insight. Java parallel stream, use the shared JVM wide fork join pool.common pool. Executing blocking I/O or network calls inside a parallel stream exhausts the shared pool, starving all other parallel streams in the entire application instance. Use dedicated thread pools for blocking operations.
Follow up when expected. A logical continuation of the incident. How does the JVM calculate default thread parallelism for fork join pool.common pool, and why is it problematic in containers?
Answer: by default, fork join pool.common pool parallelism equals available CPU cores minus 1 runtime dot get runtime dot available processors 1. In containers with small CPU limits, for example, 2 cores, the common pool has only 1 worker thread. A single blocking call completely exhausts parallel stream capacity across the entire JVM.
Follow up deeper. Experienced tester. How do you submit a parallel stream task to a custom, isolated fork join pool instead of the shared common pool?
Answer: wrap the parallel stream execution inside a custom fork join pool submit block. Fork join pool custom pool equals new fork join pool with 16. Custom pool dot submit with leads to list dot parallel stream dot for each with dot get. This isolates task execution to the 16 threads in custom pool, preserving common pool for unrelated application tasks.
Follow up 3 curveball. What is work stealing in fork join pool, and why does it fail to prevent starvation when worker threads execute blocking I/O calls?
Answer: work stealing allows idle fork join pool worker threads to steal tasks from the decks of busy worker threads. However, if worker threads execute blocking I/O like socket reads, they enter a waiting state while retaining their assigned tasks. Because the thread is blocked rather than idle, work stealing cannot reassign the blocked tasks.
Production Incident 50. After upgrading a high concurrency microservice to Java 21 and enabling virtual threads, performance degrades severely under load instead of scaling. Throughput drops, latencies spike, and OS carrier thread contention saturates CPU cores. As the on-call Java application support engineer, how do you resolve this virtual thread pinning outage?
Answer: when virtual threads become pinned to OS carrier threads during blocking I/O operations, my priority is to capture JFR event profiles, locate pinned synchronized blocks, and replace them with reentrant lock using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics post-Java 21 virtual thread migration to confirm throughput drops and latency spikes under load. 2. Check container CPU utilization in Grafana to verify carrier thread saturation. 3. Confirm whether performance degradation impacts all API endpoints or specific database or I/O workflows. Phase 2. Investigation and evidence gathering. 1. Enable JVM virtual thread pinning diagnostics by adding -djdk.trace pinned threads equals full to startup arguments. 2. Capture a 60-second JFR recording using JCMD1 JFR.startName equals VT profile settings equals profile duration equals 60 seconds file name equals /temp/vt.jfr. 3. Open /temp/vt.jfr in JDK mission control JMC and filter for JDK.virtual thread pinned events. 4. Identify source code locations executing blocking I/O calls inside synchronized blocks or native JNI methods. Phase 3. Root cause analysis. 1. Evidence collected. JFR events showed hundreds of JDK.virtual thread pinned events inside database client.execute query on a synchronized method. 2. Primary root cause. Virtual thread pinning. The application executed blocking database socket I/O inside a synchronized method, pinning virtual threads to underlying OS carrier threads fork join pool, and preventing carrier threads from unmounting to process other virtual threads. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Revert execution to standard platform thread pools, thread pool task executor, or deploy a hotfix replacing synchronized blocks with reentrant lock, then perform a rolling restart. 2. Permanent resolution. Avoid holding synchronized monitors across blocking operations that pin virtual threads. Where pinning becomes a problem, redesign the synchronization strategy or consider reentrant lock. 3. Validation. Confirm 0 JDK. Virtual thread pinned events in JFR, verify throughput scales 10 times under load, and validate carrier thread unmounting. Phase 5. Recurrence prevention. 1. Enforce JVM flag-D JDK. Trace pinned threads equals short in staging environments to flag pinned thread stack traces during automated testing. 2. Integrate static code analysis rules flagging synchronized keywords in virtual thread application codebases. 3. Conduct high concurrency virtual thread benchmarking prior to production migrations. Pro tip interview insight. In Java 21, avoid holding synchronized monitors across blocking I/O operations that pin virtual threads to underlying OS carrier threads. Where pinning becomes a bottleneck, redesign the synchronization strategy or consider reentrant lock.
Follow-up 1 expected. A logical continuation of the incident. What is the precise difference between a Java 21 virtual thread and a traditional platform thread?
Answer. A platform thread is a thin wrapper around a heavy one-to-one OS kernel thread consuming 1 megabyte stack memory. A virtual thread is a lightweight JVM managed user thread consuming bytes of heap. The JVM multiplexes millions of virtual threads onto a small pool of OS carrier threads, mounting and unmounting them dynamically during I/O blocking.
Follow-up 2 deeper. Experienced tester. Why does reentrant lock allow virtual threads to unmount from carrier threads during blocking I/O while synchronized blocks do not?
Answer. Synchronized blocks rely on legacy JVM C++ monitor locks tied directly to native OS thread addresses. When a thread blocks inside synchronized code, the JVM cannot unmount it. Reentrant lock is implemented entirely in pure Java using lock support.park, which integrates natively with virtual thread continuation mechanisms, allowing unmounting.
Follow-up 3 curveball. Why should you never pool virtual threads using a thread pool executor in Java 21?
Answer. Virtual threads are designed to be short-lived, disposable tasks created on demand. Millions can exist simultaneously. Pooling virtual threads introduces unnecessary memory retention, management overhead, and defeats the architectural design of Java 21, which relies on executors. New virtual thread per task executor to spawn new virtual threads per request.
Production Incident 51. A microservice orchestrating parallel REST API calls using completable future. Supply async freezes under heavy load. Requests hang indefinitely until client timeouts trigger. Thread dumps reveal thread pool exhaustion on the custom executor powering the futures. As the on-call Java application support engineer, how do you resolve this completable future deadlock?
Answer. When nested completable future calls on a shared bounded thread pool trigger self-dependency deadlocks, my priority is to inspect thread stack traces, eliminate synchronous get calls inside async pipelines, and enforce reactive chaining using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM transaction traces to confirm API orchestration freezes under load. 2. Check thread pool busy thread metrics in Grafana for the custom async executor pool. 3. Verify whether transaction freezes affect all orchestration APIs or specific multi-call endpoints. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using jcmd1thread.print. 2. Analyze stack traces for worker threads in the async executor pool. 3. Check if worker threads are stuck in completable future.get or completable future.join waiting for child futures. 4. Inspect orchestration source code to verify whether parent and child futures execute on the same bounded thread pool. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 20 async executor threads in waiting state at completable future.get waiting for child tasks. 2. Primary root cause. Thread pool self-dependency deadlock. Parent completable future tasks running on a 20-thread bounded executor spawn child completable future tasks submitted to the same pool and called future.get synchronously. When all 20 pool threads were occupied by parent tasks waiting for child tasks, 0 free threads remained to execute child tasks, deadlocking the pool. Phase 4. Resolution and Service Restoration. 1. Immediate Recovery Reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to clear deadlocked threads and restore immediate orchestration processing. 2. Permanent Resolution. Refactor asynchronous pipeline code to use non-blocking reactive composition methods, then compose or then combine instead of calling blocking future.get, or isolate child tasks to a separate dedicated thread pool. 3. Validation. Confirm 0-thread deadlocks under high load, verify API orchestration latency drops to 20 milliseconds, and monitor throughput. Phase 5. Recurrence Prevention. 1. Enforce static code analysis rules sonar cube flagging blocking .get or .join calls inside asynchronous execution pipelines. 2. Mandate non-blocking reactive composition patterns across all async microservice orchestration codebases. 3. Enforce dedicated, separate thread pool definitions for parent and child async execution layers. Pro tip interview insight. Calling .get or .join synchronously on a completable future inside a thread running on the same thread pool causes thread self-dependency deadlocks. Always chain asynchronous futures using non-blocking methods like then compose or then combine instead of blocking on .get.
Follow up when expected. A logical continuation of the incident. How do non-blocking methods like then compose and then combine prevent thread pool deadlocks in completable future pipelines?
Answer. Then compose and then combine register non-blocking completion callbacks instead of holding the worker thread blocked waiting for a response. When a future completes, the JVM invokes the callback asynchronously on an available thread, keeping worker threads completely free while waiting for child operations.
Follow up 2 deeper. Experience tester. What happens if you execute completable future.supply async without specifying a custom executor thread pool?
Answer. When no custom executor is passed, completable future defaults to using the shared JVM wide fork join pool.common pool. If an async task executes blocking I/O, it starves the common pool, impacting all parallel streams and default async tasks across the entire application instance.
Follow up 3 curveball. How do you handle exception propagation and timeouts in completable future pipelines using or timeout or exceptionally in Java 9+?
Answer. In Java 9+, or timeout with 2 and time unit seconds automatically completes the future exceptionally with a timeout exception if not finished within 2 seconds. The exceptionally or handle method catches that exception asynchronously, executing fallback logic and preventing pipeline stalls.
Category 3 conclusion. Concurrency and CPU engineering.
Mastering thread execution mechanics, concurrency synchronization, and thread pool isolation is what protects enterprise Java applications from catastrophic CPU saturation, thread deadlocks, and silent transaction freezes. By enforcing non-backtracking regular expressions, eliminating shared mutable state, establishing lock-free atomic constructs, and isolating worker thread pools, you build a high-throughput, deadlock-free execution architecture.
Part 1 conclusion. 51 production incidents mastered.
Congratulations on completing Part 1. We have conquered 51 grueling, real-world production incidents spanning application startup crashes, crash loop back-off loops, JVM heap memory leaks, garbage collection thrashing, 100% CPU spikes, and complex concurrency deadlocks. You now possess a battle-tested blueprint for stabilizing the core Java application runtime.
Transition. From Part 1, Java runtime to Part 2, Spring Boot and Framework runtime.
While mastering the core Java runtime and thread concurrency guarantees process stability, your application will still fail if the enterprise framework or data layer collapses. What happens when Spring circular dependencies block startup, database connection pools exhaust, or reactive web flux event loops freeze? We now transition from low-level thread execution to framework and data architecture. Part 2. Spring Boot Framework, Databases and Reactive Web Flux.
Coming up in Part 2, Spring Boot, Databases, and Reactive Web Flux.
In Part 2, we tackle incidents 52 through 100, focusing on the enterprise framework, database persistence, and non-blocking reactive streams. Category 4, Spring Boot Framework Runtime, Dependency Injection and Security 12 Incidents. Category 5, Database Connection Pools, Slow SQL, Deadlocks, ORM, and Caching 16 Incidents. Category 6, REST APIs, Microservice Routing, Time Zones and Serialization 15 Incidents. Category 7, Reactive Programming, Spring Web Flux and Natty Event Loops 6 Incidents. 49 Advanced Framework and Database Incidents ahead in Part 2.
Continue your masterclass journey.
Congratulations on completing Part 1. You are now in the top tier of production support engineers. 1. Watch Part 2 immediately. Click the link in the description below to jump straight into Part 2 Incidents 52 to 100. 2. Bookmark the full series. Check the description for links to all 4 parts of this 195-incident masterclass. 3. Subscribe and share. Subscribe to the channel and share this masterclass with your engineering team to help elevate production engineering standards everywhere. Thank you for watching Part 1. Click the link in the description below and see you in Part 2.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.